All right, let's get moving.
At Geico Auto Insurance, we handle your claim quickly, so you don't have to bum a ride to work.
All right, so what causes magnetism? We got magnets, but what causes magnetism? How do we magnetize something?
Has ever visited. No one has ever seen this place. Yet what happens here affects every one of us, every day of our lives. It's 2,000 miles beneath our feet, the Earth's molten core. Here, a vast ocean of liquid iron generates an invisible force, the Earth's magnetic field. It's what makes our compasses point north, but it does a lot more. It helps to keep the Earth a living planet. Our neighbors, Venus and Mars, have only weak magnetic fields, which means they're unprotected from the deadly radiation sweeping through the solar system. The Earth, on the other hand, exists within a vast magnetic cocoon, a force field that for billions of years has sheltered us on our journey through space. But now, scientists have made a startling discovery. It seems there's a storm brewing deep within the Earth, a storm that is weakening our vital magnetic shield.
The Earth's magnetic field has been our protector for millennia, and now it appears it's about to go away.
The Earth's magnetic field is getting weaker rapidly.
We cannot guarantee that the magnetic field of the Earth is still going to be there 1,000 years from today.
Is our invisible shield about to disappear?
The question is not if that's going to happen, it's when that's going to happen.
Could the Earth really lose its magnetic field? And what will happen if it does?
All right, so a couple of questions. Question number one, what causes the Earth's magnetic field? Question number two, how does the Earth's magnetic field protect us? What does it do? How does it work? And then there's a question number three. Obviously, the Earth's magnetic field is getting weaker, so what? Okay, so what's causing it? How does it protect us? And why is it getting weaker? Those are the questions we will get to investigate. All right, so wiping out a credit card, is it easy or is it hard? Most of you guys would think that it's easy, but is it really?
Superman the Escape blasted off into extreme ride history, earning praise for its maximum velocity, towering ascent, and seemingly endless airtime.
Foreshadow the future of roller coasters, or at least the future of the high end of roller coasters, the very technology intense, extreme experience that a roller coaster can give its riders.
All right, so the magnetic propulsion, how does it work?
This could be a caterpillar.
Oh, what?
A caterpillar drive. Magneto-hydrodynamic propulsion. You follow? No. It's like a jet engine for the water. Goes in the front, gets squirted out the back. Only it's got no moving parts, so it's very, very quiet.
Like how quiet?
It's doubtful our son not even pick it up.
What happened?
Sonic contact, Captain. Fourth quarter. Force aboard. American, Los Angeles class.
American, Captain.
Course 310.
Is the American turning to follow us?
No, Captain. American is continuing in his original course. He's continuing northwest.
He can't hear us.
All right, so this is from the movie Hunt for Red October, based on a real life occurrence, based on the novel by the same title, and the novel was based on something that happened in history. Anyway, so those of you guys who've seen the movie, give yourselves 5 points. According to the movie, the Russians have this technology. They call it the magneto-hydrodynamic propulsion unit. When it kicks in, it makes you sonar invisible. So, which means that your presence becomes unknown to the enemy. So Russians got this technology. At the time of the making of this movie, it was science fiction. Today, it's science fact. We actually have this technology. And how it works is something that we could discuss at the community college level, obviously, because the physics behind it is straightforward. The engineering, though, is top secret. It's not that easy to build something like this. So we'll discuss the physics of it. Speaking of magnetism, every single magnet is going to have 2 poles. They're going to have the North Pole and the South Pole. So the first question is, where did we get this nomenclature from? naming convention. Why is it that we call one end the North Pole, the other end the South Pole? All right, if you were wondering about this question, here's the answer, guys. When you have a magnet just like this, if you suspend it through a string, it's always going to line itself up along the direction of the Earth's magnetic field. So the end pointing towards the North Pole is known as the North Pole of a magnet. Obviously, the opposite end is going to be the South Pole. That's the reason why instead of calling one end the positive, the other end the negative, we call it the North and the South Poles. Because the magnets, left alone, suspended, they will always try to line themselves up with the Earth's magnetic field. So speaking of the Earth's magnets lining themselves up along the direction of the Earth's magnetic field, compass is a magnet, in case you didn't know. Compass is a magnet on a pivot. Always points in the direction of the Earth's magnetic field. The nice thing about the compass, it allows us to actually map the magnetic field of a magnet. Notice that the magnetic field lines will start at the North Pole of a magnet and they will point towards the South Pole. So the magnetic field lines, or the magnetic field starts at the North Pole and points towards the South Pole of a magnet. The Earth itself is a magnet, which means that the Earth itself is magnetized in essence. So imagine that there's an invisible magnet inside the Earth. The North Pole of this magnet would be pointing towards the South Pole of our geography that you're looking at. So the magnetic field lines are starting at the North Pole of this invisible magnet and pointing towards the South Pole of this invisible magnet. So the question is, what's causing the Earth's magnetic field? All right, so speaking of magnetism, let's come up with the notations. All right, so the North Pole and the South Pole. The magnetic field starts at the North Pole, points towards the South Pole. For whatever reason that I don't know, instead of using M, we end up using the letter B for the strength of the magnetic field. Proper unit is going to be T or Tesla. Earth's magnetic field points towards the North Pole, which means that the invisible magnet, whatever that is, we'll discuss that. Its North Pole is pointing towards the South Pole of our geography. The thing about magnets, though, if you take a magnet and try to isolate the source of magnetism by breaking the magnet into smaller and smaller pieces, it's always going to be magnetized. It doesn't matter how small the pieces are, it's always going to be magnetized. You break it into two halves, one end is going to be South Pole, the other end is going to be North Pole. Okay, it appears that magnetism is just going through the entire material. So the question is, where inside magnets does the magnetism originate from? All right, so we will look for the source of magnetism, or we will investigate. A couple of common knowledge points that we need to go over. You know that the light poles will repel down, light poles attract, and that's it. All right, so now let's set up the physics of it. All right, so physicists wanted to know what would happen if we place charges inside a magnetic field. How would the charges behave, right? So they created a constant magnetic field region. So the magnetic field is pointing from left to right. And into this region, well, they decided to place a charge or charges. And here's what they discovered. If the charge is static, if it's not moving, nothing happens. Nothing. All right, so if the charge is not moving, you place it inside a magnetic field or you turn on a magnetic field, nothing is going to happen to the charge. And then they decided to shoot the charge parallel to the magnetic field. If the charge is moving parallel to the magnetic field, guess what? Once again, nothing happens. No deflection. It's not going to speed up. It's not going to slow down. It's not going to change direction. Once again, nothing happens. All appearance that the magnetic field has no effect on static charges, and it's got no effect on charges moving parallel to the magnetic field. And then they decided to shoot the charges across the magnetic field. If the charges are moving across the magnetic field, now something weird happens. What happens is these charges will become deflected. But they're not going to get deflected in the direction of the magnetic field or in the opposite direction of the magnetic field. They're going to get deflected at a right angle to their motion. So you got this charge moving from left to right across the magnetic field, and then immediately it's going to experience a force, which is going to be 90 degrees to its motion. It's weird. What caused that to happen? There's no explanation for it. The only thing you know is that this is exactly what happens. So charged particles going across the magnetic field will get deflected by a force 90 degrees to its motion. So notice that this force is perpendicular to the motion. That means 90 degrees. It's moving in this direction. The force is 90 degrees to the motion itself. All right, so static charge does not experience a force. Charge is moving parallel to the magnetic field. They experience nothing. Only if the charge is going across the magnetic field, it's going to experience a deflection. And deflection is going to happen at 90 degrees to the motion of the charged particle. All right, so the charged particles moving parallel to the magnetic field, they're not going to experience anything. Only if they're going across the magnetic field, they will experience a force, which is going to be 90 degrees to their motion. Velocity vector, magnetic field. B is the magnetic field, B is the velocity vector. And notice that this is the direction of the force. All right, so how do we figure out the direction of this force? Okay, the direction of this force is determined by using something called the right-hand rule, which means that you have to use your right hand. Guys, even if you're left-handed, you will have to use your right hand. That's the meaning of it. It's a rule out of calculus. This is a bit of a loose interpretation of the right-hand rule. That's not the exact interpretation. This is the interpretation that I myself favor usually. Right, so what you need to do is you have to use your right hand, obviously. Line up your thumb in the direction of the velocity vector. Fingers line up along the direction of the magnetic field. The palm is going to face up in the direction of the force vector. Right, so the finger, your thumb is going to be pointing in the direction of the velocity vector. The fingers in the direction of the magnetic field. And then obviously the palm faces in the direction of the magnetic force. All right, so it goes like that. There are two right-hand rules, so this is the first one. So RHR, number one, right-hand rule number one. All right, so this Q represents a positive charge. All right, so there's magnetic field from left to right. This charge is moving in this direction. So these are vectors, which means that they got directions. And the force factor is going to be pointing in the opposite direction. So your thumb is going to be lined up along the direction of the velocity vector, fingers along the direction of the magnetic field, and your palm is going to face up in the direction of the force vector. Okay, so that's your right-hand rule number one. So the angle is going to be measured with respect to the velocity vector. It's pointing in that direction. Angle of the magnetic field with respect to the velocity vector. Okay. In that direction. All right, so I'm going to introduce two-dimensional representation of three-dimensional vectors. All right, if the arrow is coming out of the page, this is the notation that we use. If the vector is going into the page, this is the notation we use. In, out, in, out. All right, if you see this, it's going into the page. If you see this, it's coming out of the page. All right, so imagine that this is a magnetic field pointing into the page. I'm creating a constant magnetic field region. All right, so everything is evenly spaced. All right, so every single cross that you're looking at is going to be the magnetic field region. And then there's a charge, positive charge. And I'm going to have the charge move from up to down. So it's moving from the upward direction towards the downward direction. All right, so this is the direction of the velocity vector. So line up your thumb in this direction. All right, so it's going to be in the downward direction. Your fingers are going to be going into the page. If your fingers are going into the page and your thumb is pointing in the downward direction, force is going to be pointing to the right. All right, so the force is going to be pointing towards the right. Okay, so notice that the motion is in the downward direction and the force is pulling it to the right at 90 degrees. So it causes a deflection in that direction. All right, so it's going to get deflected in this direction. So it's going to be right here at this moment. It's moving to the right. Line up your thumb in the direction of the velocity vector. The fingers are once again pointing into the page. Your palm is going to face up in this direction. So the magnetic force is going to be 90 degrees in motion. Once again, it's going to cause a deflection. Now it's going to get deflected this way. All right, so it's going to be right here a moment later. Okay, now it's moving in the opposite direction. Once again, thumb is in the opposite direction. The fingers are pointing into the page, so which means that the force is going to be pointing to your left, to our left or your left, same thing. All right, so which means that it's going to cause a deflection, and this time this thing is going to go up all the way here. It's going to get deflected. Now it's going to be moving to the left. Again, use the right-hand rule. Thumb to the left, fingers going into the page. The force is pointing in the downward direction, and then boom, it's going to make a one perfect circle. All right, so what did we learn from that? So the charges going across the magnetic field will become deflected by a force. It's going to be 90 degrees this motion. What that means is it's going to circulate around the magnetic field. It's going to wrap itself around the magnetic field. So charged particle interacting with the magnetic field will wrap themselves around the magnetic field. All right, that's an interesting finding. That's an awesome finding. Okay, so the advantage of it is right here. This is kind of weird. So we got this charged particle going across the magnetic field. So what happens is it's going to get deflected by a force, 90 degrees this motion. So it's going to wrap itself around the magnetic field. Remember, it's magnetic field protecting us from charged particles. How does that happen? It happens beautifully. So when it's coming across, when it starts to go across the magnetic field of the Earth, it wraps itself around Earth's magnetic field. And then at the poles, it's going to get driven into the atmosphere. It's going to collide with the air molecules, exciting the air molecules in the sense that it's just going to cause this light show. You end up getting northern as well as the southern lights because of it. That's the magical. All right, we got the best answer. All right, guys, that's correct. The best answer is magnetic field will only affect the charges going across the magnetic field. So those of you guys who got this right, give yourself 5 points. All right, so what we have a positive charge moving parallel to the magnetic field lines. If charge is moving parallel to the magnetic field, what happens? Nothing. It's not going to experience a force. So C is the best answer. right, so we have a stationary charge in a magnetic field region. So what happens to the stationary charges? Nothing happens to the stationary charges. So this charge will feel no force at all. So the best answer is C. All right, so what do we have? We have a charge moving from top of the paper to the bottom of the paper. So the charge is coming in this direction. And the magnetic field is going from left to right. This is my left, this is my right. So the charge is moving in this direction. The magnetic field is going in that direction. So which means that the force would be pointing out of the page, in the opposite direction out of the page. A is the best answer. So those of you guys who got this, give yourselves 10 points. This is good. So you have a pretty good understanding of what's going on. All right. Magnetohydrodynamic propulsion.
British intelligence obtained these pictures 2 days ago. She's the Red October, the latest Typhoon class. Captain's name is Ramius. He's taken out the lead boat in each new subclass for the last 10 years.
What are these doors?
Those doors, sir, are the problem.
They really built this. This isn't a mock-up or anything.
She went to sea this morning.
This thing could park a couple of hundred warheads off Washington and New York, and no one would know anything about it until it was all over.
Just before he sailed, he posted a letter to Admiral Yuri Padorin, in which he announced his intention to fire his missiles on the United States.
We sail into history. The entire fleet is off track.
I can't believe this.
Sir, we have been sabotaged.
Russian wants to sink her. You have to do that.
Sean Connery, Alec Baldwin, Sam Neill, Scott Glenn. The hunt for Red October.
I'm telling you, he wants to defect.
I'll shake the man loose.
Right full rudder. Cancel our graveyard.
Hey, I think somebody just shot a torpedo at us.
Oh, shit. Fuck, we get the hell out of here.
Wait, where am I?
How does it work? All right, guys, let's talk about the physics of it. So here's your magnetohydrodynamic propulsion unit. Like, what does it look like? It looks like a jet engine in essence. So the water enters in and then somehow magically speeds up in this direction. Force it into your small opening. When you squeeze the fluid into your small opening, it's going to speed up automatically. So what that means is it's going to accelerate, which means that there's force acting on this water. In turn, the water is going to apply the same force back on the propulsion unit. All right? So that becomes your propulsion in essence. So the question is, how do you force the water to go faster into this smaller opening? That's where the magnetohydrodynamic propulsion unit kicks in. All right, so the physics of it is straightforward. This region is positively charged, this region is negatively charged. So, which means that the charges will accelerate in this direction under a constant magnetic field. All right, so the charge will accelerate in this direction under a constant magnetic field, thus experience the force in this direction. So these particles will get deflected. They will get deflected into the small opening, so they will accelerate into the small opening. And then obviously, you change the size of the opening, you make it smaller. So you bottleneck the opening right there. As a result, the water is going to speed up. Once again, the physics of it is straightforward, something that you could discuss, but the engineering of it was not that easy. So it's still top secret. We actually have that technology today. So that's how this works. Magnetic propulsion.
The propulsion system is a simple yet complicated mechanism. A series of electromagnets called stators line the horizontal portion of the track. As the magnets beneath the car pass over a stator, it is energized, first to attract and then to repel the vehicle.
All right, so a couple of things about this.
The ride's propulsion system is a simple yet complicated mechanism. A series of electromagnets called...
All right, so like poles will repel, non-like poles will attract each other. Right? So there's an attraction and then there's going to be a repulsion as soon as it gets over. Attraction, repulsion, attraction, repulsion. So this is going to repel, the other one is going to attract. As a result, you end up getting this acceleration out of it. It's straightforward. Okay, the only way this is going to happen though, if you could just change the polarity of each and every single magnet under tracks at will. Okay, so this is attractive. As soon as it gets over it, now it becomes repulsive. This is attractive. As soon as this gets over it, it becomes repulsive. All right, so which means that you should be able to change the polarity of each and every single magnet. So the question is, how do we do that? Mechanically, obviously, you can just spin these magnets as well, but it's not doable. Right? You got to get a bunch of people. You got to give them headphones and all that stuff, and synchronize the hell out of everyone, so they can spin and rotate these things out well. But it's just obviously it's done so fast and so quickly. I don't think anyone can keep up with something like that. So how do we change the magnetism at will, so that right at the correct moment, precise moment, you're able to change the polarity? Now it gets repelled while it's being attracted in the forward direction, and then you change the polarity, so it pushes it in the forward direction, and change the polarity of the one in front of it, so it's attracting it in the forward direction. How does that happen? All right, so under these trains, you have the permanent magnets. This is always going to be north. This is always going to be south. This is always going to be north. And the magnets on the tracks are the ones that you should be able to change their polarity at will. So the question is, how do we do that? The answer lies with this guy. All right, I want you to remember his name. His name is Oersted. I want you to remember his name forever if you can help it. It's a big deal, guys. Not for you, maybe, but it's a big deal for these guys. This guy's Danish. All right. And so the question is, what country is he from? Just because the guy is Danish doesn't mean that he's page straight. That's one of the things that I want you to notice. And if he's Danish, is he from Finland? That's the next question. The reason why I'm asking these questions is because nationality means a great deal in Europe. And there's rich history behind it. It's fairly violent. And people are extremely tribal, nationalistic. They take great deal of pride. Not only are they in their own history, but also their contributions to the general well-being of humanity in sciences and technology, as well as arts. And in fact, they take such great deal of pride in this particular guy's achievements that you're gonna find his picture in their currency. All right, so Danish, which means that this guy's from Denmark. Just remember that, it's a country. And Oersted is a physicist. He was, I think, he was teaching high school at the time. And this is 1829. This is, I think 1819 is more likely. Yeah, 1819. Physics presentation. He lined up students in front of his desk. It had some kind of a rudimentary battery, so he would just run a current through the wire, and then he would stop, and then obviously the wire would heat up. And then the students would just line up and touch the wire, and then they would get this warm and fuzzy feeling, and then next student, so everyone would be happy. And that's it. That's the entire presentation. It was trying to demonstrate that if you run a current through a wire, it's simply going to heat up. 1819. And something weird happened. There was a compass on the table. And then eventually he noticed that every time there was current in the wire, there would be a deflection in the compass. And then he noticed it. Immediately discovered that the current within the wire was causing magnetism. All right, so this is a chance discovery. This is one of the biggest discoveries in the human history, as you will find out.
Hans Christian Oersted discovered that electric currents produce magnetic forces, and that those forces always make magnets point perpendicular to the direction of the current.
So electric current is what causes magnetism. That's what Oersted discovered. Electric current is what causes magnetism. All right, so the current is going in the opposite direction. The magnetic field is going to wrap itself around the current. All right, this is going to give us a second right-hand rule. All right, this time you have to line up your thumb in the direction of the wire. You have to line up your thumb in the direction of the current. And then when you grab the wire, your fingers will curl in the direction of the magnetic field. All right, so the thumb is lined up in the direction of the current. Fingers will curl in the direction of the magnetic field. That's it. All right, so I represent the current. The current is going to be coming. The I represents the current. The magnetic field is going to be coming out of the page here. It's going to wrap around. It's going to go into the page right at that point. All right, so B represents the magnetic field. All right, so thumb is going to be in the direction of the current. The fingers will curl in the direction of the magnetic field. And this becomes our right-hand rule number 2. And Oersted, I say 1820. I think the actual date is 1819. It's not a big deal. All right, guys, it's 200 years ago. Amazing. All right, so current is coming out of the page. The current is coming out of the page. So your thumb is going to be pointing out of the page, so which means that your fingers will curl in the counterclockwise direction, right? Current going into the page, your fingers will curl in the clockwise direction. I messed this up. It should be curling in this direction. It's going into it. All right. I wonder if, okay, I didn't notice it obviously happening during the lecture and no one corrected it. All right, moving forward. All right, so we got a loop, current loop. If that's the case, all right, so magnetic field is going to come out and wrap around in that direction. And then if I have multiple loops, okay, so instead of a single loop, you can just loop it up in this direction. So it turned into a coil, just like that. So in every single loop, the current is going to point in the same direction. And notice that now it starts to act like a magnet. This is known as an electromagnet. And then what we do, you place an iron bar in the middle. what happens is iron is very easily magnetizable, so it becomes magnetized. So this becomes the North Pole, this becomes the South Pole. So it's known as an electromagnet. All right, that's how you create an electromagnet in essence. All right. You get some kind of an iron core, iron bar, and then wrap a coil around that. You run a current through it, it generates magnetism, and so what happens? Iron becomes magnetized. All right, so if you reverse the direction of the current, you're going to end up reversing the polarity of the iron bar. Okay, so now this becomes the South Pole, this becomes the North Pole. All right, so this is your electromagnet, basically. So the place in iron, run the current one way, this is the North Pole, reverse the direction of the current, all of a sudden you change the polarity, now this becomes the South Pole. And that's how the electromagnets work. All right, so the current is coming out of the page. The magnetic field is going to be curling around the wire in kind of clockwise direction, right? So A is the best answer for this one. All right, so current generates magnetism, so you can magnetize an iron bar, and that's your electromagnet. All right, so on the tracks, you got these electromagnets. You can change the polarity by reversing the direction of the current at will. And that's how the technology works.
Alignment of the system.
The ride's propulsion system is a simple yet complicated mechanism. A series of electromagnets called stators line the horizontal portion of the track.
Extremely strong field.
Mounted on the undercarriage of each car are extremely powerful rare earth magnets, so named because they come out of the earth already magnetized. As the magnets beneath the car pass over a stator, it is energized, first to attract and then to repel the vehicle.
So we have these stations at strategic locations. We induce about 480 volts, 2,000 amps into each one of these. So when the car moves onto the stator, they have an attraction and a repulsion. So this is pulling, and then it's pushing. Just like if you had a couple of magnets when you were a kid, you're turning it this way and it attracts, you turn it that way and it repels. That's in essence how the system works.
By firing at a rapid rate just ahead of the vehicle, these powerful magnets accelerate the 6-ton cars from 0 to 100 miles per hour in less than 7 seconds.
180 volts, we induce about 480 volts, 2,000 amps.
2,000 amps,
into each one
on the electric chair, it's 20 amps.
of these. So when the car moves onto the stator, they have an attraction and a
You don't want to be near any of these
repulsion. So this is pulling, and then it's
electromagnets while they're in fully operation.
pushing. Just like if you had a couple of magnets.
So what does it mean? Does it mean that it's difficult to wipe out a credit card? Does it mean that it's easy to wipe out a credit card? All right, guys, just watching the show, I kind of figured that it's probably next to impossible to wipe out a credit card. As far as I'm concerned, you should not be able to wipe out a credit card by using household magnets. All right, so that's the conclusion that I came up with based upon this. We don't use Gauss, we use Tesla in physics. And so I didn't know exactly what it takes to wipe out a credit card. Just wanted to do a demonstration when my dad was visiting from Turkey. I don't know, it's like 20 plus years ago. So we were at an electronic shop and he bought a bunch of stuff. And then we were in line waiting. And then I put my hand in my pocket, and sure enough, there was a magnet in my pocket because obviously I was in a demonstration when I was teaching. I left it in my pocket by accident. He had his credit card ready, so I said, "Dad, can I buy your credit card for a second?" So he handed me the credit card, and then of course immediately I produced the magnet. He knew what I was up to. He knows I'm crazy, so he figured that I was going to wipe out his credit card using a magnet. He said, "Don't." I said, "Dad, just trust me. I'm a physicist or not. Let me just show you something. You would think that I can wipe out this credit card using a regular magnet. It's not going to happen. Just watch it." So I took the magnet and then I moved it across the credit card back and forth a couple of times, gave it back to him. I said, "It's going to be fine." Sure enough, the magnet didn't work. The credit card didn't work. My dad was really pissed. He thought that was a practical joke. And I was really, really pissed because the Mythbusters, oh my God, did they ever get anything right? So, I mean, this is such a simple experiment. You could just see the results of it. That when it comes to electricity, I could see that they were getting confused. When it comes to magnetism, these guys were just, most of the time, they were clueless. They didn't know what these numbers meant. But as far as I could tell, I mean, this experiment, they've done a good job with this one. You're not supposed to be able to wipe out a credit card. So I decided to offer extra credit to our students, check to see if we could actually wipe out anybody's credit card. For extra credit, I ended up getting quite a few volunteers. So we went to an ATM machine just to make sure that their credit cards were working fine. So I gave them the magnet and I told them what to do with it, check to see if they could just literally wipe out their own credit cards. Guess what, guys? It didn't work. We were able to get one credit card to get wiped out and the rest of them were fine. All right, so my dad being from Turkey, I think the standards weren't the same. This is like 20 years ago. Today, you'll find it next to impossible to wipe out these credit cards using external magnets. Another thing that I want you to notice is, in order to gauge the strength of the magnetic field that they were generating, these guys were using electromagnets.
Careful. That's a Zenith digital TV you're looking at. From big to small to flat to thin, you can't escape the power of Zenith digital.
All right, so speaking of Zenith, they tried to make a comeback. After that ordeal, they tried to make their own high-definition TVs. It didn't work, so the operations were moved to Korea. I don't know what happened at Korea. They didn't succeed, so they made a late entrance into the market. And then this is the commercial that they came up with. Completely nonsensical, in the sense that evidently the quality of the pictures are so amazing that these people kind of forgot to unzip themselves. All right, so how did the TVs used to work? Well, I get. All right, so you accelerate the electron beam, and then by using electromagnets, you would just trace the beam onto the screen a couple hundred times per second. You would just trace the scan onto the screen. That's the way it used to work. So they would have to use these electromagnets for that purpose, and then they would be able to deflect the beam side to side, and then you just go side to side as you're tracing it in the downward direction, a couple hundred times per second. All right, so here's a question for you. We know that the light bulb, Edison gets credit for it. He's not the inventor, but he gets credit for it. Most people think that Edison is the guy who invented it. All right, so light bulb versus a TV, which one is a bigger invention? You know the answer, right? This is a no-brainer. The TV is a much bigger invention than the light bulb ever was. And so the question is, who invented the TV versus the light bulb? Edison gets credit for the light bulb, so who gets credit for the TV? I mean, come think of it, we know who kind of invented the light bulb, so Edison gets credit for it, but why is it that we don't know the name of the person who invented the TV? I'm going to give you a few hints. The guy's not from China, he's not from Russia, he's not from Europe, he's certainly not from Canada, he's not from South America, all right? He's not from Africa either. Australia, forget it. The guy is from the United States. Why is it that we don't know who this guy is, if that's the case? This is kind of weird because up until 20 years ago, until there was a mention of this guy in Chicago Tribune, I didn't even think of the name of the person who invented the TV. I didn't even know that there was a single person who was responsible for it. This guy's name is Farnsworth, Philo Farnsworth.
Once out of school, he headed to
And the reason why you don't know his name is not because his name is weird.
California for more research. He got some financial backers, and in 1927, in this loft in San Francisco, Philo Farnsworth made his first successful test of electronic television. He was 21 years old.
It's 1927, guys. He was 21 years old. College graduate? Not really. All right, so this guy actually came up with the idea of a TV when he was taking a physics course in high school. He was sitting way in the back somewhere during the lecture, and he was actually designing the electronics components of the first TV at the time.
With him was his new bride, Pam, a girl next door he'd married back in Utah. I'm trying to imagine what it must have been like that day in that room when those first pictures appeared on that tube.
Well, I'll tell you, it was a big thrill. These first backers, one of them used to come in and he'd slap Phil on the back and say, well, you got the damn thing to work yet? So when we got this transmission, he was in L.A., and we sent him a wire saying the damn thing works.
Compared to all the unforgettable images TV has shown in the 72 years since that day, that very first transmission was definitely underwhelming.
This is where the picture was.
It consisted of nothing more than a straight line across the screen. But as Farnsworth fine-tuned the system, he transmitted Disney cartoons, a Mary Pickford movie, and for the backers, the money men, a drawing of a dollar sign.
Mr. Philo T. Farnsworth, shown at the right, is working on the image dissector tube.
And it wasn't long before other people were looking over Farnsworth's shoulder, seeing dollar signs too, namely the big boys of broadcasting, RCA.
RCA owned all the patents for radio, and was their ambition to own all the patents for everything that had to do with communications.
But Farnsworth had already won valuable patent approval for his TV system. RCA would either have to pay him enormous royalties to use his ideas or buy him out.
There was no way he would have considered that because that was his project.
There was a court fight with RCA that dragged on for years.
All right, so RCA wanted to buy him out. He said no. He was interested in royalties. He was offered a lot of money. He figured that he was going to make a lot more money in royalties. He would have been right. He would have been probably the richest person who ever lived. Next to him, Bill Gates would have looked like a homeless person, guys. Just imagine. He wanted royalties. RCA said no. So RCA took him to court. They couldn't buy him out. RCA didn't want to pay royalties. So there was a court fight. The weird part of it is, if somebody wants to buy my Ford Tampa, if I say no, do they have grounds to sue me? The answer to that question is, they can sue you for anything, but normally a lot of these frivolous lawsuits are thrown out of court, so it's not going to go on. RCA actually had a case. They already had a working prototype of a TV. They had a physicist, a PhD, working on the idea about the same time. And the prototype was working, actually. They had a working prototype. They applied for the patent. Farnsworth applied for the patent. And it's more or less, it was about the same time. So they decided to challenge it in court. Except Farnsworth came up with the idea earlier. So the case hit the press. His high school teacher had a recollection of what happened. Remember, he was sitting in the back designing the electronics component of his first TV. So he didn't know. Farnsworth, he was like, I don't know, 16 years old, maybe 15, 16. He didn't know whether or not it would work. So he just went up to the physics teacher and said, hey, do you think this might work? The guy not understanding what Farnsworth was saying, he said, why don't you just put the stuff up on the board? Explain it to me, which he did. Except the guy didn't understand it. So he said, okay, I have no idea what to tell you. He said, let me just jot down the idea and then go talk to someone who may know a little bit more than I do. So evidently, high school physics teacher just copies down the ideas and everything else, and then goes to one of the universities nearby and talks to one of the physics professors. And the guy says, yeah, it might work. And then, so high school teacher kept that copy, which was dated. So the court fight starts, and the guy shows up as a witness and says, Farnsworth came up with the idea, I don't know, like 5, 6, 7 years ago. And then, of course, the case was decided in his favor.
Farnsworth won, but he paid a heavy price.
I don't think that it did too much for my father's health. He was pretty worn out, actually.
By now, it was the late 30s. War was coming. Government approval of commercial TV would be put on hold, and the payoff for Philo Farnsworth was slipping away.
He said, it's going to be a long war, and I think my patents will have expired by the time it's over. And it really took it out of him, because he just put his whole life force into getting television.
He was right. After the war, TV took off in America, just at the point Philo Farnsworth lost his exclusive patent rights.
Battery-powered transistorized TV.
Anybody could use his ideas now, free of charge, and they did.
He wouldn't even let us talk about television at all.
Even the word was a no-no in the house.
Yes.
He turned to other projects, spending more time with his family. He was 40 years old, worn out, disappointed, almost forgotten.
Well, he was on I've Got a Secret. Where the secret was.
Is this some kind of a machine that might be painful when it's used?
Yeah, sometimes it's most painful.
Well, he did get a carton of cigarettes for being on the show.
Here are your Winston, sir, and our eternal gratitude. I'd be out of work if it weren't for you. Thank you,
In 1969, 2 years before his death, Philo Farnsworth watched with the rest of the world as the Apollo 11 astronauts took his invention into space.
Tranquility Base here. The Eagle has landed. Rocket Tranquility.
When the men landed on the moon, they were using a special miniaturized Farnsworth image dissector to send the pictures back to us. And Phil says this makes it all worthwhile.
A statue of the kid from Beaver, Utah, now stands in the United States Capitol. The man who invented the damn thing that's inspired and bedeviled us all.
Many people have said, well, that's simple, the television idea. Anyone could do it. But you see, anyone didn't. Philo Farnsworth did.
Sad part of it, he didn't even get a penny out of it. That's what happened. By all means, he should have won the Nobel Prize in Physics, at the very least. He got nothing out of it. He got no recognition out of it. Up until Chicago Tribune was running that story on the 50th year anniversary of commercial TV, never even heard of it. Evidently, his name also got suppressed by RCA. All right, so now he's finally getting a little bit of the recognition that he deserves. Those of you guys who are Futurama fans, there's Farnsworth there in honor of this guy. And that's the end of it.
Taipei, Taiwan. Every father thinks his family is special. Lin Yuzhong's entire family is magnetic. Spoons, coins, even an iron sticks to them, defying all obvious explanations.
So the question is, what causes magnetism, right? What makes a material magnetic? Certain things are very easily magnetizable, like iron, the cobalt. Okay, guys, this is a segue video regarding magnetism. I got news for you. This got nothing to do with magnetism. I kind of thought that this was an interesting segue, and I didn't think of explaining for whatever reason. So this video from like 15 years ago, and I was teaching at engineering physics over at Harper College. And then about a few years later, somebody emailed me asking me about this video and what the explanation was. All right, it was an engineering student. This guy was working as an engineer and was still pondering about it. A couple of things. This has nothing to do with magnetism. They say it's magnetic. All right, so if it's magnetic, it's glass does not stick to something because of magnetism, obviously. this thing is, some of the stuff is plastic sticking to them. All right. For whatever reason, the skin creates this suction, almost like Spider-Man. And so it just let anything and everything sticks to the skin. All right. So because they were talking about magnetism, I decided that this would be a nice segue. All right. Despite the fact that it has nothing to do with magnetism. So the question is, what causes magnetism? What makes materials magnetic? Why is it that iron becomes so easily magnetized?
Nail is not a magnet.
No kidding, it's a nail.
Right, it won't pick up these metal paper clips, see?
Right, it's a nail.
But if I run the nail over this really strong magnet several times, the atoms inside the nail will begin to sort of line up in one direction.
And what does that mean?
Well, it means the nail can become a magnet, see?
All right, so the question is, why is it that iron is so easily magnetizable? Well, here's what we know. We know that the motion of charges, the current, the electricity is what generates magnetism. Right?
A circular loop
So the question is how?
of electric current also creates a magnetic field of this form. And so does every proton, every neutron, and every electron in the universe.
All right, so the magnetism can be traced back down to atoms themselves. The atoms are atomic magnets in essence. What's happening inside atoms are, what do you have? You got the proton, it's spinning, it's a positive charge spinning. Spin motion creates its own microscopic current loop. And by the, by the nucleus, around the nucleus, you have the electron moving around. The motion of the electron is known as a current. It becomes a current loop. All right, so the orbital motion of the electron creates this current, microscopic current loop. If there's current, there's going to be magnetism. All right, so here's what you got. You got the proton at the center. Electron is moving about the center. And what the electron is doing, the motion of the electron creates a current. The current is the motion of charges moving in the same direction. Where there's current, there's magnetism. So the magnetic field is generated by the current itself. So the orbital motion of the electrons is responsible for the generation of the magnetic field. So which means that the atoms become small magnets. On top of that, you got the positive charge at the center, which is spinning on its axis. Because the charge is spinning on its axis, it causes this microscopic current loop. So that microscopic current loop is going to generate its own magnetic field as well. So as a result, the atoms become small magnets, generating their own magnetic fields. All right, so the magnetic field is a field. It's a vector field, so it's that direction. So the direction matters, right? If the magnetic fields are pointing in the same direction, the intensity of the magnetism is going to go up. If the magnetic fields are facing in opposite directions, it becomes subtractive in a sense. So it's going to reduce the strength of the magnetic field within that region. So what do we have? We've got two atoms. All right, so these atoms are acting like microscopic magnets. And one is pointing in the opposite direction. The magnetic field is pointing in the opposite direction. The other is a magnetic field pointing in the normal direction. So when you sum up the effects of the magnetic fields in this region, it's going to add up to 0. If you can somehow get these atoms to point in the same direction, if you can get them to have their magnetic fields line up in the same direction, then the entire structure becomes magnetized. It just so happens in certain materials, it's fairly easy to get the atoms to face or point in the same direction, like iron, nickel, and cobalt. The way to do it is you have to kind of use an external magnet. So the external magnet is going to get these atoms to actually point in the same direction. So their magnetic fields will point in the same direction. As a result, the iron is going to become fairly easily magnetized. The reason why iron becomes easily magnetized, or it's easily magnetizable, is because iron already contains these small regions, which are known as magnetic domains, within which the atoms are already pointing in the same direction. All right, so within this region, all the atoms are pointing this way. Within that region, all the atoms are pointing in that direction. Their magnetic fields are pointing in that direction. So the idea is to get all the magnetic fields to point in the same direction. And for you to be able to do that, you have to use an external magnet. So by using an external magnet, you can get all these domains pointing in the same direction. And when you do so, all of a sudden this entire structure becomes magnetized.
Can you tell us what makes iron different from other metals?
Well, for one thing, iron has the ability to become magnetized.
Could you explain?
Sure. In a piece of iron, like in any metal, the atoms face in different sort of random directions.
You mean like this way and that?
Yes, so to speak.
Objection, I'm bored.
Hang in there, Mr. Savage. Continue, Dr. Fullerguest.
Well, if the atoms in iron can be organized somehow to face mostly in the same direction, that iron becomes magnetized. It would send out an invisible field of magnetism, a magnetic field, all around it.
All right, so the whole idea is to get the atoms to point in the same direction within the structure. And when you do so, it becomes magnetized.
So if animals...
Using a strong enough external magnetic field, you should be able to magnetize just about anything.
So if animals can be levitated in a magnetic field, who's going to be the first human volunteer?
People ask, well, what I can levitate a frog, or I can levitate a bead or something. Can I levitate my grandma? Well,
The answer is yes, but to levitate grandma, you got to have a magnet that is about 100 megawatts worth of power and has a diameter of, say, 2 feet. I think you could do it for, you know, $500 million.
It would be cheaper to hitch a ride on the next space shuttle.
All right, so pick out the best answer. All right, so how's magnetism generated? If you're looking at this question, there are two possible answers. And one of them is the best answer. The question is which one. All right, so magnetism is generated naturally because of some metals such as, okay, forget that. That's not the best answer. All right, so I'm looking at the magnetism generated on the atomic level by aligning all the atoms in the same direction by an external magnet. Okay, so that's one possible answer. The second possible answer is the magnetism generated on the atomic level. Magnetism is generated on the atomic level by the orbital and spin motion of the electrons and the nuclei. Okay, so either B or D. So the question is, which one is a better answer? Okay, so how's magnetism generated? The magnetism is going to be generated on the atomic level by the orbital and spin motion of these charges. In essence, how something becomes magnetic is not the same as how magnetism is generated. Magnetism is always generated by the motion of the charges. So the magnetism itself is generated at the atomic level, usually by the microscopic current fluids of the charged particles. All right, so D is the best answer in this case. Those of you guys who pick D, yourselves 5 points.
Okay, just as the atoms in a bar of iron can be organized, lined up in one direction, they can also be disorganized. Stenographer Fred, would you kindly smash the nail with the hammer, please?
I don't think I could smash it kindly.
Right, well then just smash it hard.
Okay. Yeah.
All right, Fred, now that should do it.
No more smashing?
Now that its atoms have become disorganized, the nail is no longer a magnet. See, it won't pick up any paper clips.
All right, so how does impact destroy magnetism? What happens with impact? All right, this is actually a pretty good test question. The only way you're going to be able to destroy magnetism if you can get those atoms out of alignment. All right, if the atoms have their magnetic fields facing in the same direction, obviously the thing is going to be magnetized. It's going to remain magnetized. Through impact, you can cause vibrations, which is known as heat. So as soon as the atoms start pointing at random directions, the magnetism is going to diminish, right? So that's what impact does. That's one way of doing it. So the impact is going to cause vibrations. It's going to cause heat. So by heating something else, by heating a magnet, you can destroy its magnetism.
One thing you may not know is that something that is magnetic can have its magnetism destroyed just by heating it. For example, this is an iron wire. And you can see that it's magnetic because it's being held up right now by being attached to this ball magnet. I'm going to destroy the magnetism of that iron wire by heating it. And I'll do that by passing an immense current through it. Let me just do that. Now, as it warms up, you'll see that the wire starts to sag, but I'll have to get it almost red hot before it will fall off the magnet. I'll have to put a little more current in still. Now watch, and there it goes. When it got hot enough, it destroyed its magnetism and fell off the wire. Now, of course, that I've disconnected the current, it's cooling down, and when it gets cool enough, I should be able to make it stick back to the magnet again, like that. So magnetism can be destroyed by heating, and it's restored when the material cools down again.
All right, so how does heating destroy magnetism? Heat, by definition, is the random motion of atoms and molecules. Heat is generated by the random vibration or rotational motion of atoms and molecules. That's what it means, which means that the magnetic field, the magnetic fields of atoms and molecules are facing or pointing in random directions. So when there's heat, the motion becomes randomized. So the magnetic fields of atoms and molecules start to point at random directions. So as a result, what happens? The overall effect of magnetism is diminished or reduced.
I have here something that looks like just another hunk of ordinary iron, but it isn't. This is a very rare metal, which is known as gadolinium. Gadolinium is non-magnetic at room temperature. That is to say, it will not stick to this bar magnet. But that's only because room temperature is already so hot for gadolinium that its magnetism has been destroyed. If I cool it just a little bit below room temperature, it will become magnetic again. And I can do that. I can cool it down just by dipping it in this liquid nitrogen. Watch. I just have to hold it in here long enough for it to get cold enough to become magnetic. Okay, let's try it now. And there you can see now it's magnetic. Now it's actually magnetic only on one side because I only made one side cold. If I try the other side like this, it won't stick to the magnet. Only the side that's cold will actually stick like that. So, you see magnetism can be destroyed by heating. It can be restored by cooling again in magnetic materials.
All right, so pick out the best answer. All right, so the heating is going to destroy magnetism because it randomizes the motion of the atoms in the molecules, right? So, which means that it's going to cause random vibrational rotational motions, which means that their magnetic fields will be pointing at random directions. So, if they're pointing at random directions, the strength of magnetism is simply going to diminish. A is the best answer.
What's the timeline here? As the EM field becomes more and more unstable, we'll start seeing isolated incidents.
The core, the movie, we're supposed to have an observation on that one. So, and then I turn that off.
It was a secret government program known as Project Destiny.
We're building a weapon that could generate targeted seismic events.
Designed to use earthquakes to attack our enemies.
Don't get no seismic reading.
It was a perfect, untraceable weapon.
Destiny is a go.
Until something went wrong.
That's an electrical superstorm.
Popping up all over the world.
I'll put this as simply as I can. Everybody on Earth is dead to you.
The core of the Earth has stopped spinning. The spinning core protects us from cosmic radiation. Without it, radiation will create superstorms. Microwaves will literally cook our planet. How could this have happened?
It was Project Destiny. We killed the planet.
So, how do we fix it?
We can't. The core's the size of Mars. You're talking about jump-starting the planet.
What if we could?
We're here about your legendary ship.
What would it take to get it in 3 months?
$50 billion.
You take a check?
We need you to control the flow of information.
You want me to hack the planet? I'm gonna need Star Trek tapes and Hot Pockets.
You are good. Is there anything you can't do?
Not that I'm aware of.
You're trying to save the world. It's impossible. I came here to save my wife and children. I just hope I'm brave enough to save 3.
I can't wait to get into an untested ship, go to the center of the Earth, and restart its core with 1,000 megatons of nuclear weapons. Then we outrun the biggest shockwave in history.
Hot damn.
San Francisco is in ruins.
The whole West Coast is out. That's decaying faster than we thought.
2, 1. Going in.
Whoever goes into the core is not coming back.
We're losing oxygen. Breach!
Get jot it down. Let's do it.
All right, so this question is, how does the Earth's magnetic field protect us?
About your legend.
A couple of statements here. Those of you guys who've seen the movie, give yourselves 5 points. This movie's, what is it, like 20 plus years old?
Has stopped spinning. The spinning.
So what causes the Earth's magnetic field? A lot of you guys believe that the spin of the core is responsible for it. And if you believe that, because you probably got it from this movie.
The core protects us from cosmic radiation. Without it.
So what does it do? Somehow the spin of the core is responsible for the Earth's magnetic field. And the Earth's magnetic field protects us from space radiation. So what kind of radiation does it protect us?
Simply as I can. Everybody on Earth is dead to you.
From cosmic radiation.
Cosmic radiation. What's considered cosmic radiation?
Without it, radiation will create superstorms. Microwaves will literally cook our...
All right, so which means that cosmic radiation, they're talking about microwaves. And the Earth's magnetic field doesn't really protect us from microwaves coming from space.
How could this have happened?
It was Project Destiny. We killed the planet.
So, how do we fix?
So what happens is somehow the core stops spinning. So they decided, this becomes the premise of the movie, sent a bunch of people down to the core to jumpstart it.
We can't. The core is the size of Mars. You're talking about jump-starting a planet.
What if we could?
We're here about your legendary ship.
Hot damn.
Whoever goes into the core is not...
Then we got the problems. The Earth's magnetic field somewhat vanishes because the core is no longer spinning. And the birds who use the Earth's magnetic field to guide themselves, what's the EM field, electromagnetic field? Does the Earth's magnetic field protect us from electromagnetic radiation from space? Let me tell you what electromagnetic field is. Anything from radio waves all the way up to gamma rays. All right, you got radio waves and keep increasing the frequency of the electromagnetic waves. Eventually, you're going to hit the gamma ray region. That's it. These are just waves. Prime example of an electromagnetic wave is light. All right. So, do you think the Earth's magnetic field protects us from light? If it did, you wouldn't be able to see the stars, would you? You wouldn't be able to see the sun, would you? All right. So, the Earth's electromagnetic field is not there to protect us from the electromagnetic waves coming from space. The only thing that the Earth's magnetic field can protect us from are the charged particles coming from space, not the waves.
The magnetic.
So, what's the purpose of the magnetism?
Field is
Earth's magnetic field is to protect us from charged particles coming from space.
Deep in the Earth's core. It streams out near the South Pole, loops around the planet, and then runs back into the core near the North Magnetic Pole. This is the Earth's protective force field. Without it, we'd be in trouble.
I got news for you. If we didn't have the Earth's magnetic field, there'd be no life here on Earth. There would be no atmosphere per se. These fast-moving charged particles coming from space would just knock the air molecules out into space. We gradually would lose our atmosphere.
It protects us against radiation from space. It's a little bit like being in the pod here. This shields us from the weather on Earth. The magnetic field of the Earth shields us from space weather and space radiation.
Space weather is nasty. The winds that blow through the galaxy are winds of radiation, some of the most harmful from distant exploding stars.
As well as the sun.
But there is another source which is much nearer, which is our sun. The sun itself is a thermonuclear furnace, and this flings off huge amounts of dangerous material in very large explosions. In some cases, it's about the same mass as Mount Everest actually coming towards us.
Every few hours, the sun ejects billions of tons of electrically charged particles, the solar wind. Often, the Earth lies directly in the path of this onslaught. But magnetism deflects charged particles. This means that the solar wind is unable to penetrate the Earth's magnetic shield, and so flows harmlessly around the planet. The only visible signs of this drama far above our heads are the northern and southern lights, produced when solar particles trapped in the Earth's magnetic field are dragged through the atmosphere toward the poles.
All right, so a few questions yet to be answered. What's causing the Earth's magnetic field? Is it the spin of the core? How does the spin of the core can cause magnetism? What would cause the core to spin? Which direction does it need to spin in order to generate the magnetic field that we so enjoy? On top of that, the strength of the magnetic field is actually diminishing. What's causing that to happen? What's the worst thing that can happen if it's just going to diminish briefly? Obviously, we would be exposed to charge. All right, so the Earth's magnetic field, how's it generated?
Scientists have a theory about how the core generates the magnetic field. It's based on the close relationship of magnetism to electricity. In particular, the fact that electric currents create magnetic fields.
Now, there's no electric current going through the coil to start with. The iron filings just go down like pepper in a pan. But if I turn on the electric current, then you can see the iron filings line up with the magnetic field that's produced by the current in this electric coil. So it's really currents inside the Earth's liquid metal core that we think gives rise to the magnetic field.
All right, so
scientists have a theory.
Earth's magnetic field, what generates it? Here's what we know so far, guys. The electricity is what generates magnetism. If you have an electrical current, the magnetic field is going to wrap itself around it. So what's happening within the Earth itself that causes magnetism? There's got to be some sort of a current inside the Earth itself, which is responsible for generating the magnetic field. First, there are a couple of thoughts about it, so I'm just going to take you through the history of it. Number one, you know the surface of the Earth is slightly negative charge, right? All right, so the motion of the charges is known as current. The Earth is spinning on its axis. Because it's spinning on its axis, which means that the surface of the Earth is going to act like a surface current. And so, which means that the surface current itself is going to be responsible for the Earth's magnetic field. Now that's one thought, but the Earth is spinning in this direction. If the Earth is spinning in this direction, what's happening is the magnetic field should be pointing in the opposite direction. It's pointing in this direction. So what's wrong with it? It's pointing in the wrong direction. So which means that the spin of the Earth surface current is not responsible for it. So that idea is let's just dismiss that idea. All right, so if it's not the surface currents, what then? Now we can focus on the core itself. All right, so the Earth is spinning in this direction, and the core is also spinning in the same direction. The core is made up of molten metal, and let's pretend that we got these convection currents inside the molten metal, and which means that if the core is spinning in the same direction as the Earth is spinning, then obviously now, once again, the spin of the core is in the same direction. So if the magnetic field is generated by the spin of the core, it's still pointing in this wrong direction. So that didn't work either. Only way the core is going to be responsible for the Earth's magnetic field if the core is spinning in the opposite direction of the spin of the Earth. So the question is, why would the core be spinning in the opposite direction of the spin of the Earth? Let's pretend that it does. How long do you think it's going to last? The spin is going to last against all that pressure, against all that friction. Not that long, guys. It would come to a grinding stop at some point. So if that's the case, the spin of the core cannot be responsible of the Earth's magnetic field. So if that's not the spin of the core itself, then what? The question becomes what? All right, so this is still one of those mysteries. So it's not the spin of the Earth, obviously responsible for it. Let's go to an expert to check to see what the expert says.
The Earth's main magnetic field we know to be caused by the flow of large-scale electric currents.
I mean, yeah, the current is what generates magnetism. We got that.
Inside the Earth. There are other components of the field, but the main field, the dipolar component, is associated with these currents. We don't know exactly how the magnetic field is produced. We don't have an accepted model in detail for the production mechanism.
This guy's an expert. He's about to put himself to sleep.
However,
Anyway, so we don't know. We don't know. All right, so obviously the convection currents within the core may be responsible for it. It's not because the core is spinning. This thing is really hot. You got convection currents. According to the supercomputer models, they were able to kind of trace it into the core. More than likely, we got these convection currents.
we know it's
Charges that flow in this way and that way may be responsible
somehow
for it.
related to the motion of these molten conducting materials and the rotation of the Earth. And those materials are, especially in the deep interior, primarily molten nickel and iron.
Right. The exact mechanism is not understood.
Today,
Only other thing that we know is for whatever reason,
the Earth's magnetic field
the Earth's magnetic field reverses itself.
runs from south to north, which is why compass needles point toward the North Pole. And recent lava flows record a field pointing north. But 50 years ago, when scientists measured the magnetism trapped in older lava samples, they made a startling discovery. The microscopic magnets within the lava were all pointing south.
When we go back about 700,000 years, we find an incredible phenomenon. Suddenly, the rocks are magnetized backwards.
About 1 million years.
Instead of them being magnetized to the north, like today's field, they're magnetized to the south.
It seemed that prior to 780,000 years ago, Hawaiian lava must have cooled within a global magnetic field that was running to the south and away from the north, exactly the reverse of today.
All right, so which means that the Earth's magnetic field reverses itself roughly about 800 years, once every 800 years. That's too big of a statement to make, but the reversal is something that happens. We don't exactly know what caused the reversal either. The only thing we know is we're in the midst of a reversal process. Reversals started to happen already at various portions of the Earth. And during the reversal process, it becomes weaker. That's it. So which means that we become more exposed to charged particles. The cancer rates are expected to go up about 10%. And then the Earth magnetic field is going to reverse itself and come back.
The bizarre implication was that at some point, the entire global magnetic field had done a sudden 180-degree flip.
When they say suddenly, it didn't happen overnight. It's just a gradual process.
Completely reversing direction.
All right, so this is still a mystery.
17. In the 20th century, daily life has been revolutionized with the help of small...
All right, the question is the motors, how they work.
Horsepower. 90% of all motors built today.
All right, so we're going to take a look at some applications of what we did learn last time. So let's do a quick review. So we were talking about magnetism. So the magnets generate magnetism, obviously. They will have two poles. You will have a magnetic north, and then you will have a magnetic south. So the north pole of a magnet is known as the north pole because if you get a magnet and it's suspended through a string, it's going to line itself up along the direction of the Earth's magnetic field. So the end pointing towards the north is the north pole, and pointing away from the north becomes the south pole of the magnet. So the question is, I mean, certain things are very easily magnetizable. Iron, for example, cobalt, nickel. All right, so what makes things easily magnetized? Do we have a magnetic charge? Like, do we have a north magnetic charge, the south magnetic charge or something? Where's the magnetism? Where does it come from? Compass, for example, is a magnet on a pivot. By using a compass, you can trace or map the magnetic field of a magnet very easily. So this is one of the things that you could do. Notice that the magnetic field lines start at the north pole and at the south pole of the magnet. Earth is magnetized somehow, so which means that there's an invisible magnet within responsible for the Earth's magnetic field. Earth's magnetic field is always pointing towards the north pole. All right, so you've got the magnetic field lines. Strength of the magnetic field is going to be denoted by the letter B. Proper unit that we will use, the SI unit, is going to be T. T stands for Tesla. More about Tesla later. Earth is magnetized, acts like a small magnet. It acts like a magnet, not a small magnet. All right, so obviously magnetic field lines are pointing towards the north, so which means that the polarization of the magnet responsible for the Earth's magnetic field is situated like that. Notice that the polar north is coincident with our geographic south pole masses. So the question is, what caused the Earth's magnetic field? Where do we get it from? All right, so if you're looking for a magnetic charge, like the magnetic south or the magnetic north charge, a single particle responsible for magnetism, you can keep breaking a magnet into smaller and smaller pieces. It doesn't matter how small the pieces are. It's always going to be magnetized. It's always going to have two poles. It's going to have a south pole and a north pole. In all appearance, it looks like the magnetic field lines are going right through the material. All right, so if we're looking for the origins of magnetism, where does the magnetism come from? Where does it originate from? A couple of things that we already know from life. We know that the like poles will repel, the unlike poles will attract each other. All right, so this is one of the biggest discoveries in physics at the end of the 19th century. Okay, so what looks like a light beam, if you place a magnet near it, what happens? It becomes deflected. All right, so all of a sudden it was discovered that this beam was composed of charges. By looking at the direction of the deflection, they noticed that these are electrons, meaning they're negative charges. A person named J.J. Thomson discovered this in 1897, for which he won the Nobel Prize in 1905. All right, that he discovered the electron, in essence. Now, a little bit about this thing that you're looking at. This is known as a cathode ray, which means that this is an electron beam that we were discussing before. Remember, you accelerate the electron beam and trace it onto a screen, and all of a sudden you get a TV. Well, the idea of a TV came out of this little cathode ray tube that you guys are looking at. All right, so this is how you accelerate a beam. Then using electromagnets, you just trace it onto a screen to create those images.
These are the charged plates in a cathode ray tube. Here's one that's on the top. Here's one that's on the bottom. And a stream of electrons comes through that point there. Inside of this case,
that thing is very small.
There's a high voltage grid and a little device that gives off electrons. The electrons see the high voltage, they get accelerated, and some of them pass through a small hole in the center. The ones that pass through
so in essence, which it's a capacitor.
And they will hit a screen. And when those electron beams hit the screen, causes it to glow. If I were to apply a positive voltage to the top plate, as the negative electrons went through, they would be deflected. They would go upwards as a result of that positive voltage.
Meaning that if you charge the top plate positively, what happens is the electrons will become attracted to the positive charge region. And if you charge the bottom plate positively, now they will be attracted to, once again, attracted to the positive charge region at the bottom.
On the other hand, if I were to put a negative voltage on the top plate, the electron beam would go downwards as a result of that. I can alternate the beam electrically, alternately going up and down by altering the positive and negative aspect of that beam. This is the fundamental principle in the operation of television. I get a device that causes it to deflect up and down, vertical. I can also do the same thing horizontally with two more plates that control the horizontal axis. And by combining the two, I get 45 degrees. Now, as the charged particle travels through the air, kind of it acts like an electron going through a wire in as much as it creates a magnetic field around it. If I were to bring a magnet nearby, I could deflect the beam with a magnet.
Okay, so remember, the current creates magnetism. So electron moving through space, it's going to create its own magnetic field. Current is the motion of charges moving in the same direction.
This is cool. Electricity and magnetism inexplicably connected. This is the basic principle for television. Excited electrons hit the screen, causing it to glow. They also create a magnetic field, which I can change with another magnet. Each one of these lines that you see is called a flux line, or line of magnetic flux. The closer together they are, the stronger the magnet. That phenomenon is known as flux density, the ratio of flux lines per a given area. Don't do this to your television at home. It leaves a permanent magnetic charge, which will ruin your TV set. This does not happen with plasma TVs or LCD TVs. They work on a completely different principle.
All right, there's no such thing as a magnetic charge, so it's a matter of expression, guys. Just ignore that statement. Everything else was awesome, though. All right, this one is
of an electron beam by a magnetic field today. So we have the electron tube set up with the power supply heating the filament to produce the electrons, and the acceleration voltage is right now at 0. I'm going to turn the accelerating voltage up slowly to 2 kilovolts, and this will produce a nice bright beam in the electron tube. You can see that beginning to show up there pretty well. And now I'm going to turn up the amperage in the coil to produce a uniform magnetic field across the tube with a pair of Helmholtz coils that was made here at the university. So I'm going to start now turning up the voltage on the Helmholtz coils, and we'll see what the interaction is between the magnetic field and the electrons. Right now I have about 1/4 amp of current going through the coils, now about 1/2 amp, and 3/4 amp, and now about 1 amp of current. You can see a nice deflection of the electron beam in the tube there. Coils produce a uniform magnetic field across the tube with a pair of Helmholtz coils that was made here at the university. So I'm going to start now turning up the voltage on the Helmholtz coils, and we'll see what the interaction is between the magnetic field and the electrons. Right now I have about 1/4 amp of current going.
This is cute. All right, so how does the magic happen? Okay, guys, what you're watching is related to this. Remember, if there's a stationary charge, nothing happens. If the charge is moving parallel to the magnetic field, nothing happens. If it's moving across the magnetic field, charges will become deflected. So that's the whole idea. If you get an electron beam and shoot it across a magnetic field, what's going to happen is charges will become deflected by a force 90 degrees to their motion. As a result, you end up getting that circular motion out of it. All right, so if you've charges at rest inside a magnetic field, nothing happens. Charges moving parallel to the field, nothing happens. Charges going across, they will experience a force, right? Magnetic force. The force is going to cause the charge to become deflected. For positive charges, use the right hand. Okay, so this is the right hand rule is something that comes out of calculus. This is not a calculus force. As a result, we will just get to use this one. Right? This is a different interpretation of the right hand rule. So thumb in the direction of the velocity vector, fingers in the direction of the magnetic field, the palm is going to face up in the direction of the force. You have to use the right hand for positive charges. If it's a negative charge, use your left hand. So just remember that. Right hand rule is for positive charges, the left hand is for negative charges. There's no such thing as a left hand rule. Traditionally, we use our left hands if there's a negative charge. So you can gauge which direction the positive and negative charges will move. All right. So negative charges will move in the opposite direction of the right hand rule. So here's the charge moving in this direction. So that's the velocity vector. Magnetic field from left to right. So the thumb is in the direction of the velocity vector. The fingers line up in the direction of the magnetic field. So the palm is going to face up in the direction of the magnetic force. So the force is going to be responsible for deflection. So there's an angle here that we didn't discuss before. Today, last time we built up our intuition, and today, let's express that same idea. It's a little bit more mathematical. All right, so this angle is going to matter today because there's going to be a formula that we will get to use. All right, so the example that we looked at, let's just go over the same example. So two-dimensional representation of vectors. Vector coming out of the page, vector going into the page. You got a constant uniform magnetic field region. They mean the same thing. All right, so magnetic field is going into the page. All right, so we have a positive charge moving in the downward direction. Fingers are into the page. Thumb is in the direction of the velocity vector. So the palm is going to point to the right. So that's the direction of the force responsible for the deflection. Particle is going to be here at some point. Going to the right. Force is in the upward direction. It's going to get deflected. It's going to be here at some point. It's going up. Thumb is in the upward direction. The fingers into the page. Palm is pointing to the right. So force causing the deflection is going to be to the right. And then what's going to happen is something exciting happens. Particle is going to find itself here, going to the left. Once again, thumb is in this direction, fingers into the page, palm pointing in the downward direction. So what that means is charged particle is going to circular motion instead of constant magnetic field. That's it. So summary statement. Charge is going across the magnetic field will get wrapped around the magnetic field. So they will experience a centripetal force. So the magnetic force becomes the centripetal force as a result. Which meant magnetic field will only protect us from charged particles coming from space. Charged particles coming from space going across the magnetic field will be captured by the magnetic field. All right, so they'll all experience a force, 90 degrees to their motion. As a result, they will get wrapped around the magnetic field and will be driven into the atmosphere at the poles, giving us the amazing northern as well as the southern lights. All right, mathematically, it's going to look like that. This is the angle that I was talking about. So here's your velocity vector. Here's the magnetic field. Boom, boom, boom. The force is in the opposite direction. All right, guys, this is known as a cross product. This looks like a U. This is actually a V. All right, so this is known as cross product from calculus. So you're not doing calculus. And this is the one that you guys will be interested in. Okay, so the magnitude of this force depends on the charge, depends on how fast the charge is moving. V represents how fast the charge is moving. Depends on the strength of the magnetic field. Also depends on the sign of the angle between the velocity vector and the strength of the magnetic field. All right, if this angle is 90 degrees, sine of 90 is going to be 1, so that's going to give you the maximum amount of force. If there's no angle, if this is moving along the direction of the magnetic field, angle is going to be 0. Sine of 0 is going to be 0, so there's not going to be any force. All right, so the maximum force is going to happen at 90 degrees. No force is going to happen when the angle is 0. All right, so that's the formula for that. All right, so let me check to see if there's anything else. All right, this discussion for university physics students, calculus physics. All right, so again, the angle, if it's 0 degrees, which means that the motion is parallel to the magnetic field, there's not going to be any force.
welcome to the demo prep room. We're sitting here in the dark because we're going to show you that a charged particle beam does indeed go in a circle when you put it in a uniform magnetic field. So this is an evacuated glass bulb, and there's an electron gun in it. An electron gun really just means a heated metal filament. It's easy to draw electrons off of. Near the gun that you can now see glowing orange is a little metal plate that we put at a large positive potential. So that sucks the electrons up to a few hundred volts at the plate. The plate has a hole in it so that some of the electrons keep going and form a beam that continues on until it hits the glass. Now you're seeing the beam because it's exciting a little bit of gas that's inside the bulb. You're seeing light from the gas, but it's there because the beam is shooting through the gas. So you're seeing the electron beam indirectly. Now we know that if we bring a magnet nearby, it'll deflect the beam. So here's my north-south bar magnet, and sure enough, one pole pushes it up, another pole shoots it down. If I bring it in and do these kinds of things, you can do all kinds of crazy patterns with the beam if you bring in a strong concentrated magnetic field. But what we're here to do is to create a uniform field. And that's what these two big coils are. So this is a large coil of wire on one side of the bulb, large coil on the other side. So if you put them together, you can make a reasonably uniform magnetic field on the inside. So this power supply is going to increase the current in these coils, and we'll see what pattern the electron beam takes. So here, we're going to start turning it up, and you can see it's starting to curve more and more. And right now, it looks like it wants to make a circle, but the radius is too big. It doesn't fit in the bulb. So if I keep turning it up, more and more current, bigger and bigger B field, eventually, there it is. It makes a circle. Perfect circular motion, going right back to where it started. And if I turn the magnetic field back down to zero, straight again.
All right, so problem number 2 deals with this situation. All right, so while you're studying for the next test, this is one of the standard problems that I want you guys to focus on. All right, so what do we have? We got a proton. It's going to be accelerated through within a capacitor, obviously. So this is the voltage difference inside the capacitor. And it's going to be shot out of a capacitor, in essence. And then it's going to enter a region of a constant magnetic field. Magnetic field is going to be 90 degrees to the motion or the velocity of this charged particle. So what is it that we're looking for? We're looking for the speed of the proton when it leaves the capacitor. And then we need to figure out the change in the proton's kinetic energy due to the magnetic field. And now lastly, find the radius of the circular path that the proton is going to be moving on. That's it. All right, so figure out the speed of the proton as it's entering into the magnetic field region. Figure out the change in its kinetic energy, and then just figure out the radius of this circle that it's going to be moving on. That's it. All right, seems like an easy thing to do. Believe it or not, guys, you have the background for it. I'll just put things together for you. All right, so let's figure out the speed. Check to see what the change in the kinetic energy of the proton is due to the magnetic field, and find the radius of the circular path on which the proton moves in a magnetic field. All right. All right, so this is problem number 2 from the handout. I think what I'm going to do, all right, so I'm going to skip B just for now. I think what I'm going to do is, I want to do it backward? Should I just do C? On the way, I'm going to do everything else. Okay, without you guys even noticing. All right, so what do I know? I know that the proton is going to be accelerated inside a capacitor for a voltage difference, which happens to be this number. And then it's going to be shot on into a region of constant magnetic field. So this is the strength of the magnetic field. And then just find the radius of the circular path. All right, so this is problem number 2. So here's the strength of the magnetic field. This is the voltage difference. And find the radius. Okay, so it's going to be a proton. It's a net charge. It's going to be positive charge. It's going to be a proton. Here's the mass of the proton, something that you would look up normally. And that's pretty much it. All right, so I'm going to visualize the problem. Here's your capacitor. So it's going to accelerate through the capacitor into this opening. And it's going to accelerate for a potential difference, whatever that potential was. So it's going to be shot out into this region at a given speed. Magnetic field, I'm just going to draw this. In my case, it's going to be pointing into the page. If it's pointing into the page, it goes into circular motion just like that. If it's pointing out of the page, it's going to go into circular motion in the opposite direction. That's it. All right, so, okay, yeah, it goes into circular motion in this direction. So what is the radius of this motion? Circular motion, circular path. All right. Okay, so I'm gonna do stuff my way, obviously. So I'm just gonna go after the radius. What kind of motion is this? It's circular motion. What kind of circular motion? Centripetal force does. All right, so here's the centripetal force formula. Immediately you notice that the radius is in the denominator. Okay, so all of a sudden I'm thinking, oh, okay, so this is a formula that I can explore. So I'm using a generic centripetal force formula. And centripetal force is caused by the magnetic force. All right, so that's the meaning of the centripetal force. It's the same as the magnetic force. Or centripetal force is caused by the magnetic force. Like centripetal force is the same as the magnetic force. Centripetal force is any force directed towards the center of a circle. Here's the generic centripetal force formula. All right, so any force directed towards the center of a circle is known as the centrifugal force. All right, in this case, the force directed towards the center of a circle is the magnetic force. So centrifugal force is the magnetic force. Here's the generic centrifugal force formula. Here's the magnetic force formula. All right, so here's the charge moving at this speed inside this magnetic field. This is the angle between the velocity vector, direction of the motion, and the magnetic field, right? All right, so notice that magnetic field is pointing into the page. Velocity vector is 90 degrees to it. The motion is 90 degrees to it. So what does it mean? So this angle is going to be 90 degrees. Sine of 90 is going to be, oh my God, it's going to be 1. So sine of 90 is going to be 1. All right, so now here's our magnetic field, magnetic force. Charge moving at this velocity inside this magnetic field is our magnetic force. All right, so the centrifugal force is the same as the magnetic force. So which means that this equation will have to equal to this equation. So we will equate those two. So now what do we sum for? We sum for R. Okay, so you got B squared here, you got B here. Square and B will cancel. All right, so that goes away. And then what I'm going to do is I'm going to switch these two sides because I'm looking for R. R is already in the denominator, so why not just switch sides? I'm done. That's it. I think we got numbers for everything. We know the mass, we know the speed. Do we know the speed? No, we don't know the speed. Okay, so what is it that we know? We know the strength of the magnetic field. We know the charge of a proton. We know the mass, we know the charge, we know the strength of the magnetic field. This is V, this is the speed. Do we know the speed of this charge? This is that question is no, it's not given. Welcome to life, guys. If it's not given, then we have to find it. Do we know how to find it? Absolutely do, because that was the test question from the previous task. You can figure out the speed of a charge going through a hole within a coming out of a capacitor. All right, how do you do that? Okay, so here's how you were supposed to do this. A lot of you guys kind of missed this question, but let's go over it. Number one, here's the potential difference between the plates. What that means is one plate is positive charge, the other plate is negative charge. That's the meaning of the potential difference. High voltage means positive charge region, the low voltage means negative charge region. And the voltage represents the strength, that it represents the amount of energy stored within the strength of the electric field pointing from a positive charge region towards the negative charge region through a separation distance of R. So this represents the amount of energy stored within that region. Put simply, that's what it means. All right, so energy is going to be stored within that region, so which means that if you place charges within that region, what happens? Charges will become energized, which means that they will have potential energy. If they are free to move, the potential energy turns into kinetic energy. That's the energy in motion, which allows you to be able to actually compute this V. So V, the speed, do we know how to compute it? Absolutely. We've done this like 3 or 4 times already. Conceptually, we've done it like 20 times. All right, so electric field is pointing in this direction. So the electric field acting on the charge again induces a force on it. And what happens to the charge? It accelerates, it gains speed. So by using the kinematics equations, you can figure this out, or you can figure this out using conservation of mechanical energy. Either way, it's doable. All right, so the energy is stored within this region. How do I know that? Because there's a voltage difference, so which means that the electric field stores the energy. And then when you place a charge in it, like a proton, now the proton is energized. If it's free to move, that potential energy turns into kinetic energy. That's it. So the voltage difference, boom, boom, boom. That's it. Proton within this region, energized. So that's the potential energy. Free to move, that potential energy turns into kinetic energy. Hey, the speed that you're looking for is right there. V, 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 V. All right. So that's the game that we are playing right now. So we're looking for V. So what do we know? We know that the strength of the electric field is constant inside the capacitor. Or in this case, the energy is also constant inside the capacitor. All right. Initial form of energy is going to be our potential energy. The final form is going to be kinetic. So which means that potential energy will get converted into kinetic energy, right? Here's the potential energy of the charge. Here's the kinetic energy of the charge. Solve for V. And we got it. So we got the speed. So what do? Take this and substitute back into that formula. All right, so this goes literally there. And then, boom, we're done. Okay, so the next thing you do, being a physicist, I would simplify this. I would square everything and then take the square root. So I would get a cancellation here. So it would be 2qmv under the square root divided by qb, but I don't care. All right, so at that point, I think we're done. You would just plug the numbers in. Do we have a number for everything else? I'm not going to plug the numbers in, obviously, because it's happening during a lecture. It's not multiple choice. So we got a number for Q, we got a number for M, which is good. We got a number for B. All right, so we got a number for the voltage. Okay, we got numbers for everything. So at that point, you just plug the numbers in, and then you come up with an expression. I think I have the solution for this one already printed in the lecture handout. All right, this is what I was talking about, but I don't care. All right, I don't have the numbers for it. Okay, yeah, it's right here. Man, I'm a genius. All right, it's right here, but at the same time, I'm thinking that this number may not be correct. So you may have to double check that. All right, so the only one that we didn't really answer is the one that, let's just focus on that one. Let's go back. There's part B. Okay, let's focus on this one. Okay, what is the change in proton's kinetic energy due to the magnetic field? All right, so this is the sort of stuff you will have on the test. Okay, so how much will the kinetic energy of the proton change inside this magnetic field? Now, inside the capacitor, potential energy turns into kinetic, right? So once it leaves the capacitor, it's going to enter into this region at a given speed. But look what's happening. The force is acting 90 degrees to its motion, right? If the force is acting 90 degrees to its motion, the force does absolutely no work on the charged particle. Right, so there's no work being done. The work is the process of transferring energy, which means that no energy is being transferred to the electron. It's not being transferred to the electron. It's not being taken away from the electron. So the electron gains no energy. Electron loses no energy. All right. Force needs to have a component on the direction of motion in order to transfer energy or take away energy. All right. So in this case, no energy is being taken away and no energy is being imparted on this electron or proton in this case, because force doesn't have a component on the direction of motion. The force is 90 degrees to motion. So the only thing that the magnetic field is going to do is just going to change the direction of the electron. It's not going to be able to change its speed. It's like a ballet. All right, so inspired by that little thing that you saw, now let's come up with problem number 3. Well, I'm just going to do this because there's something I want you guys to kind of focus on mathematically. Right? This is kind of interesting. Okay, so while studying for the test next week, next test, when is the spring break, by the way? Okay, no one knows. As long as no one knows, we'll continue lecturing. All right, so the problem number 3, problem number 2, problem number 3, they're extensions of each other. This time the proton turns into an electron. That's the only difference. All right. So focus on problem number 2 and focus on problem number 3. All right, so what do we have? Kinetic energy of the circulating electrons are given in terms of electron volts. They will have kinetic energy. Remember, kinetic energy is not going to change. So once again, it is a uniform magnetic field region. And then what do we have? So what's the radius of the electron's path? We kind of know how to do that. At this point, I'm not sure if we will do it differently this time. What's the frequency of the circulating electron and what's the period of the revolution? Let me change this. Let me see if I have. All right, problem number 3. No, evidently I'm keeping it as is. Okay, that's fine. It's not a big deal. All right, so kinetic energy is normally given in terms of joules. Only in atomic physics, or modern physics, we use electron volts, which means that it needs to be converted to joules. Proper unit is joules usually. All right, so strength of the magnetic field is given. So capital T represents the period of this motion. And then out of that, we can figure out the frequency of that motion. Okay, so all right, so electron volts needs to be converted to joules. Here's the conversion factor. All right, and I think somebody's computing it on the side. This is happening during a lecture. I usually don't do the numeric calculations that students usually do. All right, so what do we have? So it's circular motion, just like before. All right, so so here's what I'm going to do. Okay, so instead of doing this problem in 3 steps, let me just tell you what I'm going to do first. I'm not going to do the problem as is. I'm going to just change it a little bit. Okay, so this is the information given. All right, and normally for you to be able to figure out the period of this revolution, the time it takes for it to actually complete a single cycle, you need to figure out everything else. All right, so instead, what I'm going to do is this is the main problem, so I'm going to tackle this main problem. That's what I'm going to do. All right, so this is something that you guys have to practice. I'll show you also. I will show you where you can find the solution. Okay, because I've already worked these problems out. It's one of the solutions, one of the handouts. All right, so what I'm looking for is the period of this motion. The period of this motion is the amount of time it takes for it to actually complete a single cycle. That's what it means. Okay, so what I'm going to do is I'm going to, once again, every time I'm looking for something, I come up with an expression, one equation, single equation that has what I'm looking for in it already. Okay, so I'm going to look for an equation that has the period, the time in it. I know that this got speed. Speed is the distance over time. Did I say it's distance over time? Yeah, of course I did say that, which means that the time is going to be in the denominator of this thing. All right, so I got an expression. So that's distance over time is going to be my speed. All right, so this time that you're looking at is the time it takes for it to cover this distance, and distance is the circumference. All right, so this is the amount of time it takes for it to complete a one full cycle of motion. So the one single cycle is going to have the length of a circumference, and the time it takes for it to complete the cycle becomes the period of this motion. Circumference divided by the period. That's it. Okay, that becomes the speed. All right, so this T is what I'm looking for, the capital T that we got. Okay, so capital T is going to be our period. You know what circumference is? It's going to be 2 pi r. All right, so solve for T. Circumference is going to be 2 pi r. Okay, now let's stop at this point. Okay, so I got my unknown on the left-hand side. Now I'm going to try to figure out the rest of it. All right, so I don't know what we don't know what the radius is, and we don't know the speed. Once again, what kind of motion is that? It's circular motion. If it's circular motion, there's centripetal force. The centripetal force is going to be caused by the magnetic force. It's exactly the same as before. All right, so the angle between the velocity vector and the magnetic field is going to be 90 degrees. So that becomes, notice that magnetic field is going into the page. Sine of 90 is going to be 1, so that term drops out. You got v squared, you got v, boom, boom, boom. This is going to cancel that, so square is going to go, and then v is going to vanish. All right, and then divide both sides by m, multiply both sides by r. Okay, and then we end up getting this expression for velocity. All right, so boom, there's substitution. All right, so, and there's m in the denominator, so just pull that up. Cool. All right, I'm happy. All right, what else? Notice that the radius is not going to matter. It cancels out. Okay, that's the reason why part A of the question, part A or B. I decided that I probably don't need it, so I just skip that. So it's not going to matter. Mass of an electron is something that we know. The charge of an electron is something that we know. We also know the strength of the magnetic field, and we're done. Okay, so evidently, for the period, the radius is not going to matter. All right, every single charge, regardless of what the radius is going to have the same period, depending upon the strength of the magnetic field. So the stronger the magnetic field is, the faster the charge is going to wrap around it. That's the meaning of it. All right, so strong, regardless of the distances, the stronger the magnetic field is, the faster the charge is going to wrap around it. All right, I don't have any number for that one. Okay, if you're interested in the frequency, what you have to do is you have to take the reciprocal of that value. So whatever this is, you just invert it, and then it's going to give you the number of cycles per second, number of times it's going to go around the magnetic field per second. All right, so I don't have numbers for those. Again, I'll show you where you can find the complete solutions. Okay, hold on. Okay, the computer just flickered. Can you see what I'm looking at? Yeah. Okay, cool. Because sometimes when it flickers, evidently you can't see it. All right. Okay, let me just do this just briefly. 5 more minutes, 10 more minutes, and then I'll put you guys into groups. There's no current in this wire, right? All right, so this represents the magnetic field coming out of the page. Absolutely no current. Now notice what happens if there's current inside the wire, and the wire is within this magnetic field region, right? Notice that there's going to be deflection to the right. And then if I were to reverse the direction of the current, there's going to be deflection to the left. All right, so notice that if there's a current wire inside a magnetic field, it's going to experience a force. It's going to get deflected. Wire gets deflected to the right and to the left, depending upon the direction of the current. So the question is, what's causing the deflection? All right, so you know what's causing the deflection. It's the same as the magnetic field acting on the charges, right? Remember the charges are moving in this direction. Current represents the direction of the motion of these charges. And if they're going across a magnetic field, they will experience a magnetic force in essence. All right, so rules are the same as before. Line up your thumb in the direction of the motion of the charges. All right, fingers will be lined up in the direction of the magnetic field. Your palm is going to face up in the direction of the magnetic field. That's up in the direction of the magnetic force. That's it. So the current represents the motion of charges, net charge, which means that you have CF charges moving in this direction. And they're going right across the magnetic field. So all these charges will become deflected in that direction that we're looking at. All right, bit of a derivation. I'm not going to give you the derivation, obviously. All right, so the only thing I'm trying to say is, remember this expression, charge moving at a given velocity under the influence of a magnetic field. All right, so this velocity is or speed is total length over time, distance over time. All right, so distance over time is in the denominator, so net charge over time becomes the current, not that you care, and then you end up getting this formula that we were looking at. All right, so this is the formula that we will get to use for that one. All right, so this I represents the sea of charges moving in the same direction, so that's the current. So the current is happening along the length of this wire. L represents the length of the wire. B represents the direction and the strength of the magnetic field in this direction. And once again, you have an angle, so the angle is going to be measured with respect to the length of the wire. That's what it means. And that's it. All right, so the interpretation of this formula is the same as the previous formula. We'll try to levitate a wire. All right, so the current is coming out of the page. The magnetic field is from left to right. Wire's got some weight in the downward direction. So we're going to try to generate a magnetic force in the opposite direction. If the magnetic force is strong enough acting on this wire, we can actually make it levitate. That's what it means. If you can figure out how to do it, you can probably do a hovercraft at some point. I know how to do it. It just may require room temperature superconductors to do something like this, but let's take a look at it. All right, so this is problem number 5 from the handout. So what do we have? We got a horizontal wire, stretch of copper wire. This is the amount of current being carried. That's 28 amps. Remember, guys, it's 20 amps of current, which is being pumped into the body in order to kill someone on the electric chair. So this is 28 amps of current. So this is dangerous. Inside a magnetic field. And then we're going to try to float this wire, right? So we just want to, using a magnetic field, we're going to end up floating. We want to float this wire inside this magnetic field. All right, so what do we need? So what is the magnitude as well as the direction of the magnetic field in order to balance this wire's weight? The only thing we know is the linear density of this wire in terms of grams per meter. Okay, that's it. So that's the weight in terms of grams per unit length in essence. Okay, so it's a straightforward problem. So when we know that this is the amount of current inside the wire, we got the linear density of the wire, which is the amount of mass per length. Okay, so the mass is going to be expressed in terms of grams. So what is the strength of the magnetic field, which is going to make this flotation possible or levitation possible? How much of a magnetic field do we need for something like this? All right, so 1 gram is going to be 1,000 kilogram. So it's going to be 10⁻³ kilograms per meter. So we got our conversions right. All right, so here's the wire. The current is going to be coming out of the page. So that means the current is coming out of the page. We know it's got weight, so the weight is going to be in the downward direction. And then we want to balance the weight by a magnetic force. For the magnetic field should be directed from left to right for it to be able to generate a magnetic force on this current wire. So the weight is pulling it in the downward direction, so that's going to be mg. Provided that the magnetic field is pointing to the right, it's going to induce a force on this wire in the opposite direction. So the question is, how much magnetism required in order to balance the weight of this wire by the magnetic force? Well, the first thing I'm going to do is I'm going to sum up the force on the y direction. Magnetic force is in the upward direction, W is in the downward direction. And then the net force is what causes acceleration. Just want to make sure that there's no acceleration. Okay, guys, the interesting thing is by adjusting the strength of the magnetic field, I can literally float this wire up and down. If I get, that's what it means. So I can accelerate in the upward direction. I can also accelerate in the downward direction. In this case, I just want to make it hover at a given point. So, which means that the acceleration is going to be 0 at that point. So magnetic force is going to be the same as the weight. So the magnetic force depends on these parameters. So you need to know the strength. You need to know the length of the wire. And B is what we're trying to figure out anyway. And then you need to know the angle between the direction of the current as well as the magnetic field. Notice that the magnetic field is going to be at right angles to the current. So it's going to be 90 degrees. So this is going to be 90. All right, so sine of 90 is going to be 1. Boom, so that term drops out. All right, so this equals to that. So the right-hand sides will be equal. So what are we looking for? So we're looking for B. All right, so divide both sides by I and L. And remember, mass divided by the length is going to be the density. Charge. It's going to be the mass density. All right, so what do we know? We have the current value. We don't have the mass. We don't have the length, but we know mass per length. So this term is already given. So we know what G is. It's going to be roughly about 10. All right, so mass per length is going to be the mass density. So that's kind of the lambda times G divided by the current. And that's it. All right, that's the math portion. Okay, so it's just wanted to show you a demonstration of how to do this problem using something somewhat interesting. Okay, the interesting thing is it possible to actually get a piece of wire and make it hover in the air. Okay, so a couple of problems with this. The reaction force is going to be missing, but it's totally doable. Okay, how do I know that? All right, so this is a demo done in class. All right, this is something that we end up doing a couple of years back. This is over at Bob. These are the engineering students. All right, so, okay, so here's the weight of this wire that you're looking at. All right, I think it's 9.9 grams. Is that what it is? Yeah, this is what it is. Okay, so we end up running a current through it, tremendous amount of current, and then you bring the magnet. All right, so you got the magnet nearby. All right, so if the current is going this way, depending upon the direction of the magnetic field, either the wire is going to get pushed onto the scale or it's going to get pushed away from the scale. It's not going to hover, but there's going to be a change in weight that you're going to be able to see. All right, notice that the magnetic field is pointing in the wrong direction, so which means that the wire is being pushed into the scale because of it. All right, so we move the magnet. It goes back to its 9.9 grams. Now we will reverse the direction of the magnetic field. As soon as we reverse the direction of the magnetic field, okay, this is still being pushed inside. All right, so which means that we will have to do it again. All right, so now we reverse the direction of the magnetic field, and notice that now it's lighter, which means that it's experiencing a force in the opposite direction. Except this thing was way too heavy. The wire and attachments were too heavy. That's the reason why we were not able to provide a lift for it, because we were not able to generate a lot of current. I think the amount of current that we were able to put through it was almost, I don't know, 6 amps of current. I don't know how we were able to get the current up to that value in a lab, and everything ended up heating up quite a bit. All right, so this was too heavy for all practical purposes. Well, it was a fun little demo that we did. All right, so what can you do with this, which is kind of neat? All right, the current inside a magnetic field. Guys, the entire 20th century technology is based on it, believe it or not. All right, all the motors are usually work on this principle. Case in point, you can come up with a simple device just like that. All right, so you have this wire placed right inside this magnetic field region. You run a current through it. It's going to experience a force in this direction. It's going to snap in that direction. So what can you do with it? I don't know. Stapler maybe is one way of doing it. It could be a nail clipper. It could be a mouse trap. All right, so a simple example is that. All right, so the current is running in this direction. Line up your thumb in the direction of the current. Fingers will point in the direction of the magnetic field. Notice that there's going to be a force in this direction. So the force is going to make it snap in this direction. It's going to make it twist or spin in this direction. Other application is speakers. All right, so you got the voice coil here. The voice coil is located right here. If you're looking at the voice coil, notice that the current is going in the opposite direction. So it's coming out of the page and going into the page right here. So you push the cone into the permanent magnet, north pole to south pole. So the coil is going to be within the magnet itself. Okay, so notice that the magnetic field lines are pointing in the opposite direction here. They're pointing in the downward direction here. When the current is going into the page inside this magnetic field, all right, using your right hand, you notice that the cone is going to feel a force in this direction, right? When the current is going into the page, it feels a force in this direction. Now the magnetic field at the bottom is pointing in the downward direction, and the current is coming out of the page. Under the circumstances, once again, using the right-hand rule, boom, what's happening is it's going to experience a force in this direction. All right, so you can make the cone vibrate back and forth by reversing the direction of the current. For example, whenever somebody speaks, obviously you want to be able to capture that voice. And in order to duplicate the voice, you have to just repeat the frequency. Like if I'm hitting a note, which is 600 cycles per second, which means that you should be able to reverse the direction of the current within the cone 600 times per second. As a result, you end up getting this vibration. Once again, the speakers is another example of this. The main example of it is the electric motors that make the technology possible, 20th century technology possible, the motors. Just about anything and everything that's worthwhile having has motors in it, mechanical devices that I'm talking about. All right, this would have been one of the labs that we would have done in class. It's a fun little thing. So just creating a tiny little motor. All right, so you end up getting this coil, a wire. This is a copper wire. You have a permanent magnet right here. It's a strong enough magnet. And then what you do is it's just preparing these contact points. Okay, and then it's got the coil right here. All right, so he's gonna place the coil right there, and then the magnet is gonna go right underneath. All right, this is a hands-on experiment. All right, so now what he's going to do is obviously he's got a battery, so he's going to run current through the entire structure. So the current is going to go through the coil, and then obviously everything is the same wire, and then it's going to go back into the battery in essence. So battery is going to energize the entire circuit. Okay, so what's going to happen is as soon as the current starts to run through the coil, notice that the coil is inside the magnetic field, right? But if the current is going this way, if the magnetic field is going in the upward direction, all right, so what happens is this coil is going to end up experiencing a force in this direction. All right, if it's at an angle, what happens, this is going to experience a force in this direction, and that's going to experience a force in that direction. So if you can just get it to spin initially, what's going to happen is it's going to experience a constant torque, and it's going to start to spin. Right now, everything is parallel, so nothing's going to happen. What you need to do is you need to just flick it and get it to start moving first. And then it's going to keep on moving until the battery runs out of energy. All right, so treat it as an electric motor. Okay, when you're looking at something like this, it looks deceptively easy. And the physics is not that easy to see when you're looking at something like this. Number one, for you to be able to get it to start, obviously you have to kind of flick it. And then somehow it gets energized, it's going to keep spinning. Okay, so it's a simple demos kind of look like this. But if it's your car engine, this and that, it gets up there, there's a reason for it, that is, you will find out. Okay, so, all right, so what's causing the spin motion? All right, so let's study this. Okay, so here's the loop that we will have this loop spin or keep spinning within this magnetic field, right? That's the whole idea. All right, so the current is going in the downward direction. Line up your thumb in the direction of the current. Fingers pointing in the direction of the magnetic field. So your palm is going to give you the direction of the force. So this is going to experience a force. All right, let me just use this. Here, it's going to experience a force in this direction. So it's going to experience a force in this direction. All right, here the current is going up. And the magnetic field is, once again, from left to right. It's going up. Magnetic field is left to right. So it's going to experience a force in this direction. Okay, so what's going to happen is this thing is going to spin with respect to this pivot point. So which means that it's going to experience a torque, rotational force. All right, so it's going to experience a rotational force until this is perfectly lined up in this direction, right? So it's going to spin, and then until it's lined up in that direction. So when it's lined up in that direction, what happens? The current is still going in the upward direction. And okay, so it's going to feel a force in this direction, and then what's going to happen? It's going to keep spinning, and then it's going to be just like that. Now, when its area, which is, it's got an area, I don't know, I'm going to express the area as a vector in this direction. Guys, the area has a size also. Anything with area is going to have direction. Okay, take a look at this book. Okay, it's got a size, so it's got magnitude. I can face it this way and that way. So I can put a vector that indicates the size, and I can keep changing direction. So the area is a vector. So when the area of this loop becomes parallel to the magnetic field, all right, so that when the area of the loop is in the same direction as the magnetic field, guess what? At that point, there's no magnetic force acting on it. So it will come to a complete stop at that point, all right, if there's a continuous current acting on it. Okay, so I'll try to give you a better picture of it shortly. So the only thing you need to know is it's going to experience a torque, all right, and it's going to spin. It's going to experience a force. It's going to spin until, all right, so it's going to feel a force in this direction. This portion is going to feel a force in that direction. So the entire structure is going to spin, and then at that point it should come to a stop, but it doesn't. So the question is, why not? All right, so I'm not going to bore you with the mathematical details of this one because you guys are not university physics students. University physics is engineering physics for physics and engineering students. So you guys are taking conceptual, you guys are taking college physics. The only thing you need to know is it's going to experience a torque. All right, so torque is a rotational force. And in terms of the torque that it's going to experience, the terms that I'm interested in is torque is going to be related to current. It's going to be related to the cross-sectional area of the loop. And it's going to depend on the strength of the magnetic field. And there's this angle that you got. All right, so whatever that angle is, we'll explain what that angle is. So you know that you got the current, you got the area of the loop, and you got the magnetic field going through the loop. All right, so this expression that you're looking at, all right, so the area of the loop times the current. Area of the loop times the current. All right, so is known as the magnetic dipole moment. All right, so this is the term that we're going to focus on. All right, so this area of the loop times the current within the loop, is known as the magnetic dipole moment. Speaking of the loop, you can have a single loop, single wire loop, or you can just wind it up. You can have multiple loops of it. All right, so number of loops times the amount of current within each and every single loop times the area of this loop is known as the magnetic dipole moment. Okay, it sounds like a really abstract concept, which is kind of abstract. At the same time, it's a simple enough concept. It tells you how much the loop is going to act like a magnet. That's the meaning of it. All right, this is a bit of a magnetization factor. When you have a current loop, what that tells you is this loop is going to act like a magnet, in essence. All right, so this loop literally becomes a magnet. Okay, how much this acts like a magnet depends on the number of turns that you have, the amount of current that you put into the loop, and that depends on how big the size of this area is, which is going to be intercepting the magnetic field, guys. That's it. All right, so that's the meaning of it. So magnetic dipole moment literally represents the magnetization of a current loop. How much it acts like a current, how much it acts like a magnet. Let's put it this way. It's going to be a vector. It's going to be 90 degrees to the surface area. It's going to point in the direction that the area is facing. All right, and so this tells you how much this loop acts like a magnet. I'm just going to call it the magnetization factor in essence. All right, so what creates it is literally the current within this loop is going to make it act like a magnet. So what would happen if I take this loop and then place it inside an external magnetic field? The magnetic field is going in this direction, right? So here's the direction of the magnetic field. And here's the, I'm going to say the magnetic field generated by the loop. Okay, so I know I'm taking liberties with physics at this point, but it's pretty close to the meaning of the mathematics at this point. This is how much this loop acts like a magnet. So this would be the term that acts like a magnetic field generated by this loop. And here's the external magnetic field, right? So what's going to happen? So which means that if there's an external magnetic field, the loop is going to try to line up its magnetic dipole moment in the direction of the external magnetic field by experiencing a torque. So it's going to end up experiencing a rotational force in this direction. So it's going to try to line its magnetic dipole moment up in the direction of the external magnetic field. Man, that was a long blah, 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 blah. Okay, so what's going to happen is when you have an electric motor, in essence, it's a loop of wire just like this one is. It's got a magnetic dipole moment, which means that as soon as current starts to run through it, it's going to act like a small magnet. It's going to act like an electromagnet, in essence. And then if there's an external magnetic field, it's going to try to line itself up. It's going to try to line its magnetic dipole moment in the direction of the external magnetic field by rotating in that direction, by spinning in the direction of the external magnetic field. All right, so that's the story. So it's going to experience a torque in the direction of the external magnetic field. All right, so the torque can be expressed in terms of magnetic dipole moment, tendency of this loop to act like a magnet, cross B, that's for engineering students, which is the same as this expression that you're looking at. So the torque that it's going to experience is going to depend on this magnetic dipole moment, which is mu, times speed, the strength of the external magnetic field, times the sine of the angle between the magnetic dipole moment and the external magnetic field. That's it. All right, so what does it mean? So it says that the torque is going to come about right here. So it's going to experience a torque in this direction. In this case, the magnetic field is going in this direction, reverse the angle in this case. And the magnetic dipole moment is pointing in that direction. So torque is going to come about when the magnetic dipole moment tries to align itself with the external magnetic field. All right, so magnetic dipole moment is going to represent how much a loop of wire is going to act like a magnet. And it's going to try to line its magnetic field tendency with the external magnetic field. And that's going to cause the torque, in essence. All right, so that's it. That's the explanation that I'm going to go for. All right, so this normal represents the direction. All right, okay, let's take a look at this. This requires a bit of an explanation. All right, guys, this is a loop of wire. This is a two-dimensional representation of a loop. So current is coming out of the page, it's going into the page, so you got a loop of wire, right? So as the current is coming out of the page, use the right-hand rule. So it's coming out of the page from my perspective. And the magnetic field is to my right, so which means that the force is going to be in the opposite direction. And here the current is going into the page. Magnetic field is to my right, force is in the downward direction. So what's going to happen is this portion of the wire is going to get pulled up in that direction, and then this is going to get pushed down in that direction. So the entire structure is going to spin as soon as it spins. What happens? Notice that this force is pushing the wire in the upward direction. This force is pulling the other section of the wire in the downward direction. At this point, there's zero torque, which means that this thing just spun and stopped. That's what it means. Okay, so the normal also represents the direction of the dipole moment, right? So what happens is when the dipole moment lines itself up in the direction of the magnetic field, at that point, the torque stops. There's no reason for it to keep spinning. So therein lies the problem in real life. Okay, when you do these small demos in a physics lab, everything works fine, but when you try to get your car's motor to work using electronics, it's get a little bit more complicated because now you're trying to move things around. Okay, so how do you get this loop to keep spinning if that's the case? All right, the way to do it is, okay, notice that you got these half rings, and then you got the brush or whatever. All right, at this point, what's going to happen is it's connected to if this is the car's motor, there's a battery, so the battery is just going to energize the entire circuit. The current goes up, current comes down, and obviously depending upon the direction of the current, this is going to experience a torque, so it's going to rotate in this direction, trying to line its magnetic moment up in the direction of the external magnetic field. And then notice that as soon as its magnetic dipole moment is along the direction of the external magnetic field, at this point there's no torque, but then again there's no current in the circuit either, because these half rings, notice that you got these half rings are no longer touching the brush. So because there's no current within the circuit, at that point there's no torque acting on it, so it's just maintaining its rotational motion because there's rotational inertia. Right? As a result, what's happening is it's just going to keep spinning, and then eventually the half rings will touch the brush. It's going to get energized, and then it's going to get spun in that direction. And then as soon as the magnetic dipole moment is in the same direction as the magnetic field, at that point there's no current, so the rotational inertia is going to take over, and this thing is going to keep spinning. So the real life is a little bit more complicated than that little laboratory demo. Okay, so let me check to see if I missed something. Okay, no. All right. I think this is the last thing that I'm going to do. And then I'm just going to give you guys the task. All right, so we talked about the origins of magnetism. All right, so you can trace the magnetic field to atoms. The atoms act like small magnets, microscopic magnets. All right, so that's why I said. So magnetism is generated by the motion of the charges. The current is what generates magnetism, right? So you got a single electron moving about the proton, so that's your hydrogen atom. Boom. And then this motion is known as current, so the current is what generates magnetism. And also at the center, you got a positive charge. It's spinning on its axis. So its spin motion is also generates this microscopic current loop. So it's going to generate its own magnetic field as well. All right, so it's a simplistic story, but it kind of makes sense. All right, so this is how the magnetism is generated at the atomic level. So which means that each and every single atom can potentially act like a microscopic magnet. So if you can just get these atoms to face in the same direction, the thing becomes magnetized. I'm talking about iron or nickel or cobalt or whatnot. Okay, so that's a simplistic picture of it. Okay, so now I want you to see what I'm talking about in light of what we discussed. Okay, so the magnetic dipole moment of a hydrogen atom. Hydrogen atom is everything in physics. This is the simplest model of an atom, and so that's the one that we use in developing our theories usually. All right, so the electron is moving in this direction, so it creates this current loop. So the current is what generates magnetism. And guess what? All right, guys, by definition, this is a magnetic dipole in essence. Each and every single atom is a magnetic dipole, which means that magnetic dipole tells you how much it acts like a magnet. It's going to act like an atomic magnet in essence. All right, so the meaning of the magnetic dipole moment is what creates is a current loop, and that loop needs to have an area. That's it. So it's a combination of both of them. So we got the current is generated by the motion of this electron, and notice that it's making a small loop. So this loop has its area, and then of course it depends on the number of loops that you have. In this case, we don't have a current wire. Number of loops in this case is going to represent the number of electrons. If you have one single electron, n is going to be 1. If you got 2 electrons, it's going to be 2, and so forth. All right. Okay. So while we're talking about that, think of it this way: there's a little bit of physics here, which is kind of interesting. If one electron is moving in this direction, the magnetic dipole moment due to this one is going to be pointing in the opposite direction. If you have a second electron moving in the opposite direction, it's going to have a magnetic dipole moment pointing in the opposite direction. So all of a sudden, that atom is no longer magnetized. Okay. So this represents the magnetization factor of this atom. So it depends how much an atom is going to act like a magnet. It depends on the number of electrons that it got. Just that's one of those factors that you have to consider. All right, so here we got the hydrogen atom, and it's going to be 1 because there's only one single electron. Got it? All right, so how would you do a problem like this? This is one of those cute problems. You know that the electron is going to be moving, right? Area of this circle is straightforward, so it's going to be pi r squared. We're done with that. Okay, if it's a hydrogen atom, it's got a known size. It's going to be half an angstrom, so you can calculate that. But the question is, you can calculate the area. So the question is, how do you figure out the current generated by the motion of this electron? All right, so the current is the net charge per second, how fast the charges are moving in the same direction. So it's going to be net charge per time. Net charge is a single electron, so that's the unit charge moving in the same direction. And the time is literally the time it takes for it to complete a single cycle. So that's going to be the period of this motion. Okay, we've done this problem without you guys noticing. Okay, so the time is something that you can figure out if you knew the speed of this charge. Okay, and time is the period of this motion. You can figure out the period of this motion if you knew the speed. Remember, speed is the distance over time. So the distance is going to be the circumference. It's going to be the circumference per time. So circumference divided by the period is going to be the speed. And then, obviously, for us to be able to figure out the period, we need to know what the speed is. And you can figure out the speed knowing that this is circular motion, which implies that there's going to be centripetal force. And this centripetal force is going to be created by the electrostatic force. All right, so speed, circumference divided by the period. Reciprocal of the period is going to be the frequency, blah, blah, blah. All right, we'll figure that out later. All right, so the speed. All right, so let's come up with an expression for the speed. I think this was your, if this was in-person education, this would have been a test question because I'm giving tests online. This wasn't really worth it. All right, so centrifugal force is caused by the electrostatic force, right? From that, you can figure out the speed. We've done this problem in class before. All right, so the electrostatic force, so you're interested in the absolute values of the charges. All right, R and R squared and R will cancel. And then divide both sides by M. Take the square root. And we came up with an expression for speed. If you were to use numbers at this point, you'd probably get about 5 million miles per hour. And then I would just substitute that into this formula. All right. And then from that formula, I would get the frequency reciprocal of T and then plug it into that formula. And then what do we do? And then multiply everything by E. Charges would cancel, and then I would get a current value for that. And then you take the current, okay, just plug it into that formula. Being a physicist is fun. All right, and then simplify it. And then keep simplifying it. And then plug the numbers in and blah, blah. All right, and then it works out. Okay, details aren't that important for you guys because you're not engineering students. The only thing I want you to know is notice that this hydrogen atom acts like a magnet. All right, so how much it acts like a magnet is denoted by its magnetic dipole moment. All right, that's just a magnetization factor. So what do you think is going to happen to this hydrogen atom if there's an external magnetic field acting on it? So what's going to happen is this hydrogen atom, because it acts like a microscopic magnet, it's going to line its magnetic field up in the direction of the external magnet. All right, so by using a strong enough external magnet, I can line these atomic magnets in the same direction. As a result, I can magnetize something. Okay, so that's how iron gets magnetized, the nickel gets magnetized, and so forth. Okay, let's do a fast review of the stuff that we need from this chapter. Okay, guys, there's like 20 minutes of more lecture that I need to do, but I'm gonna make that part of the video for you guys to watch. It's straightforward, so I'm getting tired, so I'm not gonna do that. I'm just gonna finish this up, and then I'm gonna give you guys your test. Okay, so I'm already gave you the problems to focus on. The rest of it, just we'll approach it from a conceptual perspective, all right? Just watch the rest from the video. Okay, so you guys already done a review on this one, so let me just go over what I have. Okay, so what's the formula representing strength of the magnetic field at the center of a loop? Okay, we didn't do that. Okay, so let's ignore that. All right, so here's the formula for the magnetic force acting on a charged particle. So this is the one that I'm focusing on. So here's the net charge right there. It's moving at this speed, which is this. All right, so here's the strength of the magnetic field right there. And theta is the angle between the direction of the motion and the external magnetic field. All right, so that's what the angle represents. All right, so we got the north and the south poles. Where do we get the terminology from? Okay, obviously, if you have a magnet, if you suspend through a string, it's always going to line itself up in the direction of the Earth's magnetic field. Right, the end pointing towards the north is the north pole of a magnet. All right, so the next question is, how do we know that the magnetic field lines start at the north pole of a magnet and end on the south pole of a magnet? Okay, so you can actually, by using a compass, you can actually map this field. The compass is a magnet on a pivot. It's always going to point in the direction of the magnetic field lines, right? So by using a compass, you can map the field. All right, so the charges at rest will not experience that magnetic force. Charges moving parallel to the magnetic field will not experience the magnetic force. Only charges going across the magnetic field will experience the force. The force is going to be 90 degrees to their motion, right? Provided that they're going across the magnetic field. So here's your right-hand rule. The purpose of the right-hand rule is to figure out the direction of the magnetic force. So it gives you the direction of the deflection. All right, so what do we have? We got a charged particle moving from the top of this page towards the bottom under the influence of a magnetic field from left to right. Using the right-hand rule, thumb is in the dump direction. The fingers are pointing to the right, so which means that the force is going to be coming out of the page. All right, so this is the direction of the force. All right, so what do we have? The current is coming out of the page. We have to use the right-hand rule number 2 for this one. So the thumb is going to be pointing in the direction of the current, and then you will curl your fingers in the direction of the magnetic field. All right, so you grab the wire, all right, line your thumb up in the direction of the current. The fingers will curl in the direction of the magnetic field. So this one is going to be pointing in the counterclockwise direction. Okay, so the Earth's magnetic field is going to protect us from charged particles and charged particles. Only charged particles going across the magnetic field will become trapped by the magnetic field. Okay, so this is a test question. What I'm asking is not only knowledge, but also justification. Charged particles going across the magnetic field will experience a force, right? At 90 degrees to their motion. So which means that they're going to be forced to actually go in a circular motion. So which means that they will get trapped by the magnetic field. So they will just circle around the magnetic field. Eventually they will get driven into the atmosphere at the poles. Okay, so magnitude hydrodynamic propulsion unit. Okay, I need a visual explanation for it, which I did, so it's not that important. So that's the application of the right-hand rule number 1. Okay, so the formula for the magnetic force acting on a single charged particle, we just discussed that. Okay, so moving forward, what else do we have? What's the angle represent? This is the force. No, this is the current moving along the length of the wire. And it's under a magnetic field, so it's going to experience that force. The wire is going to experience a magnetic force in this direction. So the angle represents the angle between the direction of the current and the external magnetic field. So we got that. All right, so the magnetic moment formula is this one. It's going to tell you how much a loop, the current loop is going to act like a magnet in essence. So it depends on the amount of current, depends on the size of the area of the loop, and then it depends on the number of turns that it's got. All right, so the proper unit, not that it's important, you've got currents, it's going to be expressed in terms of amps. You've got the area, it's going to be square meters. So what happens to the magnetic moment? If you increase the current, the magnetic moment is going to go up, right? So it's going to become more magnetized in essence. So what happens to the magnetic moment if you increase the radius? If you increase the radius, what happens? You increase the area. Area goes up, magnetic moment goes up. All right, so it's 20 and 21, they mean the same thing. So increase the radius, current goes up. Increase the radius, area goes up, magnetic moment goes up. So those are the answers to 20 and 21. What did Oersted discover? Oersted discovered that the current causes magnetism. All right, so right-hand rule number 2 is going to give you the direction of the magnetic field generated by the current. If the current is coming out of the page, we discussed that. Using the right-hand rule number 2, you know that the magnetic field is going to be in the counterclockwise direction. If you reverse the direction of the current, now it's going to be in the clockwise direction. Okay, so what else do we have? All right, so I'm just going over the stuff that we covered. All right, so electromagnet, how does it work? Guys, electromagnet is an application of the Oersted's discovery. Obviously, the current is what generates magnetism, right? So if you have a single loop, you're not going to notice, but if you have multiple loops, all of a sudden you notice that this section is going to act like a North Pole. This section acts like this magnetic South Pole. If you place something easily magnetizable in the metal like iron, it's going to become magnetized immediately. So this end becomes the North Pole, this end becomes the South Pole. You reverse the direction of the current. Immediately, you will reverse the polarity of this magnet. All right, so using electromagnet or using regular magnets, can you wipe out credit cards? And no, they're not strong enough, obviously. But if you have a strong enough magnet, you can certainly wipe out a credit card. That was more of a discussion of how to use an electromagnet. All right, so magnetism is generated by the atomic particles. So the question is how the current generates magnetism, right? That's it. The current is the motion of electrons around the nucleus, and the nucleus also spins on its axis, so also creates its own microscopic current loop. So if there's any sort of current loop, it's just going to generate magnetism. Iron is very easily magnetizable because it's got regions within which the atoms are already facing in the same direction. So if you can get all these atoms point in the same direction, atoms, magnetic fields point in the same direction, the entire structure becomes magnetized. All right, so the heating destroys magnetism because heat by definition is generated by the random vibration and rotation motion of molecules, right? So if you're heating something up, in essence, you're causing random vibration and rotation motion within molecules, so which means that they're going to start to point at random directions. So their magnetic fields will be pointing every which direction. So which means that the effects of magnetism is going to be reduced. All right, so is it possible for the Earth's magnetic field to be generated by the surface currents? No, because if magnetic field generated by the surface currents would be pointing in the wrong direction. Earth is spinning in this direction. You know, the surface is slightly negatively charged. Magnetic field, due to that motion, would be pointing in the wrong direction. So that's not the main component of the magnetic field. All right, so the next question is it possible that magnetic field is generated by molten metal deep inside the Earth? Well, it is possible, but not because of its spin motion. All right, because it can only spin in the direction of the Earth's spin, obviously. Spinning in the opposite direction doesn't make sense. If it's spinning in the same direction, magnetic field that it's going to generate is going to be pointing in the wrong direction. All right. So you got convection currents within the core itself. They must be moving in a direction which is responsible for those magnetic fields. So that's the best estimate that the supercomputer model was able to come up with. So why is this magnetic field getting weaker? Obviously, the current must be changing direction, whatever that current is or wherever that current is. And that's the only explanation that we can come up with. All right, so what else do we have? Okay, we kind of talked about that, so let's focus on that one. All right, so we had a discussion about that. All right, wow, a little bit more. Magnetic dipole moment is going to be related to the number of turns. So if you increase the number of turns, you're going to be able to increase the dipole moment.